The universe is much more alive and mysterious than the calm picture we usually imagine. Planets moving smoothly around the sun, comets flashing across the dark sky, and stars sparkling like scattered diamonds. But the real wonders of our cosmic neighbourhood aren't just in the familiar paths we can see. They also stretch far above and sink deep below. High above, huge bursts of gamma rays shoot toward the northern parts of our galaxy, showing violent events happening billions of light years away. Far below, invisible streams of gravity twist and pull, quietly guiding the journey of our solar system as it drifts through the sea of stars. So before we begin, share in the comments where you're joining from and what time it is for you right now. Then get ready, because we're about to take a trip through the universe that just might change the way you see it forever. Space is not quiet at all. It is a restless ocean filled with invisible storms, and within those storms are countless tiny bullets racing endlessly. These bullets are what scientists call cosmic rays. Despite their name, cosmic rays are not rays of light in the ordinary sense. They are actually particles, so small that you cannot see them, yet carrying enormous amounts of energy. They zip through the universe at nearly the speed of light, striking anything in their path, including our planet Earth. You're being struck by them even as you read these words, though you feel nothing. The story of cosmic rays begins in some of the most powerful and violent places in the universe. Many are born in the fiery deaths of stars. When a star many times heavier than our Sun runs out of fuel, it collapses and explodes in a supernova. This explosion is so intense that it can outshine an entire galaxy for a short time. In the chaos of that blast, particles are hurled out at unbelievable speeds, and some of them become cosmic rays. But not all cosmic rays have such well-known origins. Some seem to come from mysterious places we do not fully understand. They may emerge from the hearts of galaxies, from monstrous black holes that swallow matter and spit out streams of energy. Others might come from gamma-ray bursts, which are colossal explosions thought to be the most powerful event since the birth of the universe itself. When scientists study the paths of these cosmic rays, many appear to rain down on us from above the solar system, especially from regions beyond the Sun's northern pole. Most are protons, which are the building blocks of atoms, while some are heavier atomic nuclei like helium or iron. A smaller fraction are electrons. No matter their type, they are all dangerous travellers from far beyond our world. Cosmic rays strike Earth from every direction, but scientists have noticed something strange. There is a heavier concentration coming from above the ecliptic plane, that is, from above the flat disk in which the planets orbit the Sun. Why does this happen? No one knows for sure. Some experts think it may be because our entire solar system is moving through a sort of cosmic headwind, a stream of particles and fields blowing through our part of the galaxy. Others believe it is caused by the shape of the galaxy's magnetic fields, which act like invisible channels, steering these particles more strongly from certain directions. Whatever the reason, the puzzle remains unsolved, and each new observation brings both answers and fresh questions. One of the most important guardians we have against cosmic rays is something called the heliosphere. The heliosphere is like an invisible bubble that surrounds the entire solar system. It is made by the solar wind, a constant stream of charged particles blowing outward from the Sun. Think of it as a giant shield stretching far beyond Pluto, the outermost of the well-known planets. When cosmic rays come racing in from interstellar space, they must first cross this protective shield. Here, they encounter the solar wind and the Sun's magnetic fields. Sometimes these defences deflect or slow them down, but not always. The strength of the heliosphere changes depending on the Sun's activity. Every 11 years, the Sun goes through a cycle of rising and falling activity. During solar minimum, when the Sun is calm and its surface shows few sunspots, the solar wind weakens. At these times, more cosmic rays slip through the shield and pour into the inner solar system, especially from the north. During solar maximum, when the Sun is stormy and active, the shield is stronger, blocking many of the incoming rays. To learn more about this invisible shield and what lies beyond it, humanity sent 2 spacecraft on long journeys into deep space, Voyager 1 and Voyager 2. Launched in the year 1977, these spacecraft were originally designed to visit the giant planets, Jupiter and Saturn for Voyager 1, and Jupiter, Saturn, Uranus and Neptune for Voyager 2. But after completing their missions, they kept flying, heading toward the edge of the solar system. Voyager 1 became the first human-made object to cross into interstellar space. It passed the boundary of the heliosphere near its northern edge, and when it did, it recorded a sudden jump in cosmic rays. This sharp increase showed that it had entered a place where galactic radiation was no longer slowed or blocked by the sun. It was like stepping out of a quiet room and suddenly being hit by the roar of a storm. The fact that Voyager 1 encountered such strong cosmic rays from above adds weight to the idea that we are moving through a cosmic headwind, or that the galaxy's magnetic fields are uneven, guiding radiation more strongly in certain directions. Even though we live deep inside Earth's own protective magnetic field and atmosphere, cosmic rays still find ways to reach us. Researchers study them using balloon experiments high over Antarctica, where the thin air allows detectors to catch more particles, and with ground-based monitors spread across the world. One of the most curious findings is that more cosmic rays hit Earth's polar regions than anywhere else. The explanation once again lies in magnetic fields. Charged particles like cosmic rays do not move in straight lines. Instead, they spiral along invisible lines of magnetic force. Earth's magnetic field guides these particles toward the poles, where they plunge into the atmosphere. When they smash into the upper layers of air, they trigger beautiful natural light shows, the auroras. In the northern hemisphere, it is called the aurora borealis, or the northern lights, while in the south it is the aurora australis, or the southern lights. These displays look like glowing curtains, rippling waves, or green and red fire dancing across the night sky. They are one of the most breathtaking reminders that we live in a universe filled with unseen storms. Among all the cosmic rays, some are so powerful that they leave scientists stunned. These are called ultra-high energy cosmic rays. To understand how extreme they are, consider this. The most advanced particle accelerators on Earth, such as the Large Hadron Collider in Europe, can smash particles together at incredible energies. But the universe has particles that carry millions of times more energy than that. These ultra-high energy cosmic rays appear to fall from above the plane of the Milky Way, but their exact sources remain unknown. Some theories suggest they come from the violent hearts of distant galaxies, where supermassive black holes fling out matter at near-light speeds. Others propose that they come from gamma-ray bursts, those short-lived explosions that release more energy in a few seconds than our sun will emit in its entire lifetime. The truth is, no one knows for sure. Their origin is one of the greatest mysteries of modern astrophysics. But to solve these puzzles, scientists have built enormous projects dedicated to catching and studying cosmic rays. One of the largest is the Pierre Auger Observatory in Argentina, which spreads detectors over an area bigger than some countries. Another is NASA's Alpha Magnetic Spectrometer, a powerful detector mounted on the International Space Station. The Alpha Magnetic Spectrometer has made a particularly intriguing discovery. It has detected an unusual excess of positrons, which are the antimatter twins of electrons. These positrons also seem to come from above the ecliptic plane. This strange finding has led some scientists to wonder whether they might be the result of dark matter, the mysterious invisible substance that makes up most of the universe's mass, annihilating itself nearby. Others believe they could come from unknown cosmic engines just beyond the reach of our telescopes. While cosmic rays are fascinating for scientists, they are also dangerous for astronauts. On Earth, our thick atmosphere and strong magnetic field protect us from most of their harmful effects. But in space, beyond these shields, the situation is different. Cosmic rays can pass straight through the walls of spacecraft. They can pierce the bodies of astronauts, damaging their DNA and increasing their risk of cancer. They can also interfere with delicate electronics, causing malfunctions in spacecraft systems. This presents a serious challenge for the future of space exploration. As humanity prepares to send astronauts to Mars and beyond, protecting them from cosmic radiation is one of the most pressing problems. Engineers are developing new kinds of shielding, smarter spacecraft designs, and better strategies for long-duration missions. The patterns of incoming cosmic rays, when and where they are strongest, are being studied carefully to help guide these solutions. There is another ingredient of the universe, something quiet, invisible, and easily overlooked, that actually makes up a huge part of everything. This mysterious ingredient is neutral hydrogen. Neutral hydrogen may not shine, sparkle, or roar like other cosmic objects, yet it is everywhere. It is one of the most widespread elements in the entire universe, and without it, stars could not exist at all. You can think of it as an enormous, invisible ocean stretching beneath the main flat disk of our home galaxy, the Milky Way. Unlike the glow of stars or the energy blast from black holes, neutral hydrogen does not put on a show for the naked eye. It does something far subtler. It hums, almost like a faint whisper across space. This whisper comes at a very special frequency, 1420 MHz. To a human ear, it would not sound like anything at all, but radio telescopes can pick it up. Astronomers describe it as the 21 centimetre line, a signal that has become one of the most powerful tools in all of astronomy. Neutral hydrogen, often written as Hi, is the simplest atom in existence. Imagine a tiny speck with just one proton at its centre and one electron orbiting around it. That is all. No extra pieces, nothing fancy. It is the most basic building block of matter, the kind of atom that filled the young universe shortly after the Big Bang billions of years ago. On its own, one atom of hydrogen is much too small to notice. You could never point a telescope at a single atom, but the universe contains billions upon billions upon billions of them. When these atoms gather together in huge clouds, something remarkable happens. They start to give off faint radio signals. These signals are what astronomers detect when they tune their giant radio dishes to that 21 centimetre wavelength. The 21 centimetre line is not just a piece of trivia. It is the key that allows astronomers to see the unseen. Ordinary telescopes which collect visible light cannot pierce through every part of the galaxy. Dust clouds block their view, and stars outshine faint gases. But radio waves can travel through dust, meaning hydrogen clouds hidden deep within the galaxy suddenly become visible to us. By mapping the 21 centimetre line, scientists can trace the shapes and movements of gas all across the Milky Way. They can watch how hydrogen drifts, swirls, and collects into clumps that will eventually give birth to new stars. It is like switching on a special night vision mode that reveals the hidden framework of the galaxy. The most surprising discoveries are often made beneath the galactic midplane. If you think of the Milky Way as a great spinning disk, the midplane is the central flat surface where most stars and gas lie. But below this surface, in the darker and quieter regions, lies a hidden world. Here, the conditions are calmer and colder than in the bustling main disk. Instead of chaos, explosions, and the bright glare of stars, you find silence, emptiness, and purity. These are places where hydrogen clouds can linger undisturbed for millions of years. Radio surveys, such as those from the Hi4PI and Galpha High projects, have revealed that hydrogen below the galactic plane is not spread evenly. Instead, it gathers into enormous layered clouds. Some of these stretch across thousands of light years, twisting and curling like giant waves frozen in motion. These clouds drift slowly, pulled and sculpted by the rotation of the Milky Way and by the invisible tug of its gravity. One of the strangest features uncovered is something called the galactic warp. Imagine a spinning record lying on a turntable. If the record were perfectly flat, the Milky Way's disk would be even and smooth. But in reality it is bent. On one side it dips downward, and on the other side it arches upward. Our own solar system is not standing still on this record. It is sliding downward into the bent part of the disk. Right now, we are heading toward one of the densest regions of hydrogen in the southern sky. In a sense, our star and all its planets are surfing across this warped galactic wave, drawn by the pull of the hydrogen ocean beneath us. At this point, someone might ask, why should we care about invisible hydrogen clouds? The answer is simple. Neutral hydrogen is the raw fuel of stars. Every star in the sky, no matter how bright or faint, began its life inside a cloud of hydrogen. Long before it lit up, the gas gathered, cooled, and collapsed under the pull of gravity. Slowly, atoms squeezed together until nuclear fusion began in the centre, releasing the light we see. Without hydrogen, none of this could happen. So when astronomers study the hidden hydrogen beneath the galactic disk, they are not just looking at empty gas. They are looking at the very first stage of star formation. It is like watching the opening scene of a cosmic drama, long before the main characters appear on stage. In some ways, these gas clouds act like the memory of the galaxy. They carry scars from past events, collisions, mergers, and flows of material that shaped the Milky Way into what it is today. Just as a person's skin may hold scars from old wounds, the hydrogen carries echoes of the galaxy's long and violent history. Just as a person's skin may hold scars from old wounds, the hydrogen carries echoes of the galaxy's long and violent history. Not all of the hydrogen beneath the disk formed there naturally. Some of it is the wreckage from galactic collisions. Over billions of years, the Milky Way has swallowed smaller galaxies. As these smaller companions were torn apart by gravity, streams of their gas were pulled downward into the halo of our galaxy. Two examples are the Sagittarius dwarf galaxy and the Magellanic Clouds, both neighbours of the Milky Way. Long ago, their gas was stripped away, forming wispy trails that continue to fall toward us even today. These streams crash into the surrounding halo gas, creating shock waves and compression zones. In some places, this sparks new star formation. In other places, it smothers it. Among the most puzzling objects are the so-called high-velocity clouds. These are massive clumps of neutral hydrogen racing through space at incredible speeds. Unlike normal gas clouds, they do not match the steady rotation of the Milky Way. Instead, they seem to be on their own paths, as though flung out or dragged in by some mysterious force. Where did they come from? Astronomers are still unsure. Some believe they are leftovers from ancient galactic collisions. Others suspect they are fragments of material blown out of the Milky Way by supernova explosions, now falling back in. And some even suggest they may be fresh gas from the cosmic web, vast rivers of intergalactic material slowly feeding our galaxy like gentle cosmic rain. One of the most famous examples of these strange objects is the Smith Cloud. This is a colossal body of neutral hydrogen currently approaching the Milky Way from below the disk. The Smith Cloud is massive enough to form at least 1 million new stars. It is racing toward us at nearly 240 kilometers per second. To put that in human terms, that is hundreds of times faster than a speeding bullet. In about 40 million years, the cloud will slam into the Milky Way's disk. When it does, the collision could ignite a spectacular burst of star formation in the southern half of our galaxy. It will be as though someone struck a match and set off a brilliant chain of new suns. Even before this grand event, the Smith Cloud is already sending shockwaves into the hydrogen layers beneath the disk. These ripples give astronomers valuable clues about how gas behaves in deep, cold regions of space. By studying the Smith Cloud, scientists can better understand the endless cycle of gas falling in, stars being born, stars dying, and gas being returned to space. Our understanding of neutral hydrogen is only beginning. New technology is about to open up this hidden world like never before. The most exciting of these is the Square Kilometre Array, which will be the largest radio telescope ever built. Once complete, the SKA will give astronomers an incredibly detailed three-dimensional map of hydrogen throughout the galaxy. They will be able to trace the smallest ripples in the hydrogen sea, watch how gas flows around the galactic warp, and even measure how it interacts with magnetic fields and cosmic rays. In many ways, it will be like scanning the ocean floor on Earth. Instead of sand, rocks, and fossils, the cosmic ocean will reveal buried streams of gas, scars of past collisions, and records of the galaxy's history. We often lift our eyes to the sky searching for brilliance, the dazzling stars, glowing nebulae, or the fiery aftermath of supernovae. But beneath all of that lies a hidden world. Neutral hydrogen is like a ghostly fog, a silent sea stretched across the galaxy. It does not shout, it whispers. Its voice comes not in light but in faint radio waves, carrying stories of creation, destruction, and rebirth. It is the silent witness to everything that has ever happened in the Milky Way. Without neutral hydrogen, there would be no stars, no planets, and no life. It is the foundation on which galaxies are built, the seed from which stars grow, and the memory that holds the history of cosmic events. For many decades, physicists have been chasing something that seems almost like a ghost, a particle that has never been seen, never been touched, but which, if it were ever found, would completely reshape how we think about electricity, magnetism, and perhaps even the entire fabric of the universe. This strange and mysterious particle is called the magnetic monopole. To understand why this idea is so important, we need to step back and look at the basics of how magnets usually behave. Everyone who has played with a bar magnet in school knows that a magnet always comes with two ends. One end is called the North Pole, and the other is the South Pole. If you snap that bar magnet into two pieces, each piece still has both a North Pole and a South Pole. If you break it again, the smaller pieces will also each carry both poles. No matter how much you cut it, you can never isolate a single pole. This behavior seems to be a fundamental law of how magnets work in our universe. Yet the idea of the magnetic monopole suggests a completely different possibility. Instead of always coming in pairs, a monopole would carry just one pole alone. It would be purely north or purely south, standing alone without its opposite. At first glance, that might seem like nothing more than a curiosity, an oddball idea in physics. But if such a particle really exists, it would change everything about how we understand electricity and magnetism. It would be like discovering that all this time we had been reading only half of a story. Magnetic monopoles are not just the fantasies of overactive imaginations. They come naturally out of some of the most advanced and ambitious theories in modern physics. For instance, in the grand unified theories of physics, often shortened to GUTS, magnetic monopoles appear as natural consequences of the mathematics. These theories attempt to merge the different forces of nature, such as electromagnetism, the weak nuclear force, and the strong nuclear force, into one single, elegant framework. In these grand blueprints of the universe, monopoles are predicted to exist as stable particles. They also emerge in certain forms of string theory, another deep and far-reaching idea that tries to explain all of reality as tiny, vibrating strings of energy. In both these grand attempts to explain the cosmos, magnetic monopoles show up as important characters. That alone tells us something. These particles are not whimsical inventions, but rather expected actors in the deepest possible description of the universe. So, the idea is serious. But if they exist, where should we look for them? The universe is vast, and monopoles are expected to be very rare. The leading theories suggest they were born during the earliest fraction of a second after the Big Bang, in the same way that other exotic relics such as primordial black holes may have been created. These are not lightweight particles like electrons or neutrinos. Instead, monopoles are predicted to be extremely heavy, perhaps thousands of times heavier than the familiar proton that makes up the heart of every atom. Because of this immense mass, monopoles would not zip through space at the wild speeds of cosmic rays. Instead, they would drift slowly, pulled along by the magnetic field lines of galaxies. Imagine them like heavy beads sliding gently down invisible strings of magnetism stretched across space. This leads scientists to a natural question. Where in the galaxy are the magnetic field lines cleanest and easiest to follow? Our home galaxy, the Milky Way, is a crowded and noisy place. Near the central plane of the galaxy, there are countless stars, glowing clouds of hot plasma, and turbulent storms of magnetic activity. Exploding supernovas, radio bursts and winds from young stars all add to this cosmic noise. Searching for monopoles here would be like trying to hear a whisper in the middle of a roaring stadium. But if we look below the flat disk of the Milky Way, toward the southern galactic pole, the situation changes. The further we move from the busy galactic plane, the calmer space becomes. There are fewer stars, less glowing plasma, and much quieter magnetic conditions. In these calmer zones, the galaxy's magnetic fields stretch out more smoothly, like long strands of spaghetti laid out neatly instead of tangled in a chaotic bowl. This is why many scientists believe the best place to search for monopoles is in the southern reaches of the galaxy, beneath the disk where the noise fades away. The hunt for magnetic monopoles is already underway, and it involves some of the most extraordinary instruments humanity has ever built. One of these is the IceCube Neutrino Observatory, located deep beneath the ice of Antarctica. Here, sensors are buried in the clear ancient ice to watch for faint flashes of light. Normally, IceCube looks for neutrinos, tiny ghost-like particles that rush through Earth all the time. But the same system could also catch the glowing trails of a magnetic monopole drifting through the ice. Another remarkable experiment is Antares, placed in the deep waters of the Mediterranean Sea. Just like IceCube, Antares is designed to watch for faint traces of high-energy particles. The ocean water acts as a giant detector, ready to light up if something extraordinary passes through it. So far, neither IceCube nor Antares has found definitive evidence of a magnetic monopole. The detectors remain silent. Yet physicists are not discouraged. They argue that perhaps Earth itself is not the best place to look. Closer to home, our planet's environment is far from ideal for such delicate searches. Earth is constantly bathed in the turbulent magnetic winds of the Sun. Solar flares, storms, and waves of charged particles create a loud magnetic background. This noise can easily drown out the faint, subtle signals of a monopole drifting by. That's why many researchers suggest we need to look beyond Earth, far from the reach of the Sun's restless magnetic field. A spacecraft placed below the ecliptic, the flat plane where planets orbit the Sun, could gaze toward the galactic South Pole, a region where the magnetic environment is cleaner. In such a calm zone, a slow-drifting monopole might finally reveal itself. Besides giant detectors in ice or water, scientists have also dreamed of cleverer and smaller tools. One of the most promising is the superconducting loop. A superconducting loop is a ring made of special material where electricity flows forever without any resistance. This is one of the strangest and most beautiful behaviors of superconductors. Now here is the trick. If a magnetic monopole were ever to pass through such a loop, it would leave behind a permanent mark by changing the flow of electricity. It would be like a toll gate counting a traveller passing through a road. The loop would quietly say, "Something unusual just went by." Imagine a future where fleets of robotic probes carry these superconducting loops into the calmer southern regions of our galaxy, scanning the quiet magnetic silence for the faintest disturbances. Each loop would act like a watchful eye, waiting for the ghostly visitor. Some researchers have even wondered whether monopoles might sometimes become temporarily trapped by the magnetic fields of planets. Earth itself has a long magnetic tail, shaped like a comet's tail, stretching far into space. Perhaps a wandering monopole could be caught in this magnetic net, only to be released during a violent geomagnetic storm. If that is true, it means that some of the clues we are looking for could already be close to home. The challenge is figuring out how to detect them among all the other cosmic activity. Still, the quieter, wider stretches of interplanetary space remain the most promising hunting grounds. A monopole, drifting slowly and steadily in these calm zones, would leave behind only the faintest of traces. This is why future space missions may include ultra-sensitive magnetometers, devices designed to measure magnetic fields with extreme precision. If tuned finely enough, they might finally catch the telltale fingerprint of a monopole. At this point, you might be wondering, why is everyone so obsessed with this elusive particle? Why spend decades searching for something that might not even exist? The reason is simple, but profound. If magnetic monopoles are ever discovered, they will confirm some of the boldest predictions physicists have been making for over half a century. But more importantly, they may help answer one of the most puzzling mysteries of nature. Every single electron in the universe carries exactly the same amount of electric charge. Whether the electron is in a galaxy billions of light years away or inside your own body, its negative charge is identical to every other electron. This strange consistency seems almost miraculous. It is as if nature uses one single mold to stamp all electrons. Why is this the case? What force or law of the universe makes sure that charge is always the same? Some physicists believe the answer lies with magnetic monopoles. Their existence could explain why electric charge is quantized, why it always comes in fixed, identical amounts. In that sense, monopoles would not just be missing puzzle pieces, they might be the very key that locks the puzzle together. The dream of physics is to bring all the forces of nature into one unified description. Right now, we know of 4 fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. These are the basic interactions that govern the entire universe. Finding the magnetic monopole could be the breakthrough that finally unites them. It would be the bridge connecting electromagnetism to the nuclear forces, and perhaps even to gravity. The discovery would be nothing less than revolutionary. For now, the monopole remains hidden. The great detectors beneath the ice and sea have yet to catch it. The spacecraft that might one day fly beneath the galactic plane have not yet been launched. The superconducting loops are still dreams on engineers' drawing boards. But the hunt continues. Scientists keep refining their tools, scanning the skies and thinking of cleverer ways to listen for this ghostly particle. They believe that in the cold, dark basement of the galaxy, far to the south of our familiar skies, the secret may be waiting. Somewhere in that quiet darkness, drifting slowly along the invisible lines of the galaxy's magnetic field, there may lie the particle that could finally tie together the story of the universe. Stars sparkle softly like lanterns scattered across a dark blanket. Planets drift slowly in their paths, and comets sometimes blaze past like brief messengers. From the ground, it all feels peaceful, as if nothing ever disturbs the great stillness above. But the truth is far stranger and far more active. Space is not a silent ocean. It is a storm, filled with countless invisible travelers rushing in every direction. These travelers are not spaceships, nor are they anything we can see with our eyes. They are particles, tiny fragments of matter and energy, that zoom through the galaxy at nearly the speed of light. Among them are cosmic rays, ghostly neutrinos, and ions stripped of their electrons. They do not move in neat lines or settle into predictable patterns. Instead, they dart about like arrows fired from unseen bows, colliding, scattering, and flowing across the cosmic sea. For a long time, scientists assumed that these particles rained down upon us evenly, arriving with no preference for any direction. After all, if the universe is vast and full of energy, should not its messengers reach us in a random, balanced way? Yet careful measurements have revealed something puzzling. The flow is not even. Particles sometimes prefer one path over another. They appear to arrive more from certain directions, as if some regions of the sky are sending whispers, while others remain quieter. This imbalance has a name. Scientists call it anisotropy, a word that simply means not the same in all directions. In other words, instead of being a smooth, even drizzle of particles, the cosmic rain is a little heavier in some parts of the sky and a little lighter in others. And the most curious part? A surprising number of these extra arrivals seem to come from beneath the plane of the Sun, the invisible circular sheet in which our solar system makes its orbit around the centre of the Milky Way galaxy. To understand why this discovery is so strange, we need to pause and look more closely at the idea of anisotropy. Imagine standing outside during a rainstorm. If the rain falls straight down, soaking everything evenly, you would say it is isotropic, same everywhere. But if the rain seems to blow harder from the east than from the west, leaving one side of you wetter than the other, then the rainstorm is anisotropic. The same applies in space. If particles arrived evenly from all sides, we would say the cosmic shower is isotropic. But if more particles come from one direction than another, the shower is anisotropic. Scientists began noticing this unevenness decades ago, but only with today's sensitive instruments can we truly map it. Some of the most powerful detectors for this work are the IceCube Neutrino Observatory, buried deep in the Antarctic ice, and satellite-based detectors like PAMLA and the Alpha Magnetic Spectrometer 02, also known as AMS-02, orbiting high above Earth. These machines are built to listen to the faintest footsteps of the universe's tiniest travellers. Year after year, they record the arrival of particles, carefully noting their direction and energy. What they find is remarkable. When the results are drawn on a map of the sky, a pattern emerges. Certain regions, especially those beneath the galactic plane, show a small but consistent excess of high-energy arrivals. These are not random blips or temporary glitches. The anisotropy persists, appearing again and again across many years of observation. One of the most important lessons in science is to be cautious with patterns. Sometimes what looks like a signal is just noise, accidental coincidences that vanish when more data is collected. But in this case, the imbalance is too persistent and too statistically strong to be dismissed as chance. Think of it like tossing a coin. If you flip it 10 times and get 7 heads, you might think nothing of it. It could simply be luck. But if you flip it 1,000 times and it still leans heavily toward heads, you know something deeper is at play. The particle anisotropy is like that coin toss. After countless flips recorded by observatories, the uneven flow remains. Importantly, this imbalance does not seem to be caused by the Earth itself. Our planet's magnetic field, powerful as it is, cannot explain the large-scale directionality observed. Nor do the measurements appear to be mistakes from the instruments. Instead, the evidence points to something real happening out there in the galaxy. But what could cause it? Why would the universe prefer to send more particles from one direction than another? One of the leading explanations lies in the vast, invisible threads of magnetism that weave through our galaxy. The Milky Way is not just stars and gas. It also contains enormous magnetic fields, stretching across hundreds of thousands of light years. These fields act like invisible rivers, tugging on charged particles and bending their paths. Cosmic rays, which are mostly protons moving at incredible speeds, are especially sensitive to these fields. Just as a charged ball would curve if you rolled it through a magnetic loop, cosmic rays are constantly being nudged, twisted, and redirected. If the southern half of our galaxy, the region beneath the plane, contains stronger or more tangled magnetic structures, it could guide more particles in our direction. Some scientists imagine this region as being filled with remnants of ancient supernova explosions. When a massive star dies, it can hurl shockwaves of plasma across space, leaving behind long-lived magnetic scars. These scars, frozen into the interstellar medium, may still be shaping the movement of cosmic rays today. In a way, every particle that reaches us may be following the ghostly fingerprints of stars that exploded millions of years ago. Picture the galaxy as an invisible subway system. Particles do not always travel straight. Instead, they follow hidden tracks made of magnetic lines. Some of these lines may naturally funnel particles upward toward the solar system. If so, the anisotropy is not a mystery at all, but the signature of these cosmic rails. Another possibility reaches even deeper into the history of the Milky Way. Our galaxy is old, over 13 billion years, and throughout its life, it has consumed smaller galaxies like a giant predator. These galactic meals leave behind streams of stars, clouds of gas, and halos of dark matter. Some of these leftovers now drift below the galactic plane, in the southern regions where the anisotropy seems strongest. Among these remnants may lie exotic objects. Black holes that once belonged to devoured galaxies could still be active, spitting out jets of high-energy particles. Collapsed stellar cores, pulsars spinning like cosmic lighthouses might also contribute. Even dense knots of dark matter, if they decay or interact in unexpected ways, could release floods of particles. If such relics exist below the plane, they may act like cosmic accelerators, firing particles upward toward us. This would explain why we see more arrivals from the southern sky. It is the direction of ancient galactic scars still echoing their presence through streams of high-energy messengers. There is yet another factor to consider: our own movement. The solar system is not standing still. It orbits the center of the Milky Way at roughly 220 kilometers per second, carrying us around the galactic core every 225 million years. At this moment in cosmic history, our system is also drifting slightly downward through the galactic plane, heading toward the southern regions. This motion itself creates a kind of optical illusion. Imagine driving into a rainstorm. Even if the rain is falling straight down, it feels like more drops are hitting the front windshield than the back. In physics, this is called the Compton-Getting effect, and it works the same way with cosmic particles. Because we are moving into the southern sky, particles arriving from below appear slightly more energetic than those from above. This does not fully explain the anisotropy, but it adds another layer. Our movement sharpens the differences, helping scientists separate real cosmic flows from mere observational biases. By combining data from observatories in both hemispheres and over many years, researchers are now building three-dimensional maps of particle flows around our solar system. These maps are like weather charts, showing invisible winds of energy sweeping across space. And what they reveal is astonishing. The region beneath us, below the galactic plane, is far more active than once believed. Instead of being quiet and empty, it seems alive with energetic structures, hidden accelerators, and tangled fields. Even more intriguing, the anisotropies in cosmic rays appear to line up with other signals. For example, the Fermi Gamma Ray Space Telescope has detected gradients in gamma rays, bright emissions that also appear stronger in the southern sky. The IceCube Observatory has spotted bursts of neutrinos that seem to echo the same pattern. It is as if multiple messengers, cosmic rays, gamma rays, and neutrinos, are all pointing toward the same hidden sources below the galactic plane. Are these alignments mere coincidences, or are they telling us that something truly remarkable is lurking below the galactic disk? Scientists do not yet have a final answer, but many suspect we are seeing hints of undiscovered astrophysical structures, perhaps long-lived remnants of collisions, magnetic funnels guiding energy, or even exotic processes like dark matter decay. Whatever the cause, the message is clear. Space beneath our feet is not silent. It is whispering with stories, carried by streams of particles that arrive from favoured directions. At first glance, studying the uneven arrival of invisible particles might seem like an abstract pursuit, far removed from daily life. But in truth, this research has deep importance. Understanding these flows helps scientists improve models of space weather, the storms of particles and radiation that can endanger astronauts and damage spacecraft. For future explorers travelling beyond Earth, knowing the shape and direction of these cosmic winds could be as essential as sailors once knowing the currents of the sea. It also reveals hidden details of our galaxy's structure, mapping regions too faint or obscured to study with traditional telescopes. And perhaps most thrilling of all, anisotropy may point the way toward new physics. If dark matter, the mysterious substance making up most of the universe's mass, decays or interacts in ways we have not yet seen, the evidence may arrive not in bright light but in the subtle unevenness of cosmic rays. Most of us grow up learning that tides are about the ocean. We think of the sea pulling back to reveal wet sand and seashells, only to roll in again with foamy waves. Teachers explain that this happens because the moon's gravity tugs on Earth's waters. Some people might also know that stars near black holes can be stretched apart by extreme tidal forces. But tides are far more than something that makes waves crash on a beach or shreds unlucky stars near cosmic monsters. Tides, in the language of the universe, are about how gravity stretches, bends and reshapes matter across unimaginable distances. These invisible pulls ripple not just through seas but through entire galaxies. Gravity is the great sculptor of the cosmos. It does not only keep planets locked to stars or stars bound to galaxies, it also pulls at the very structure of galaxies themselves. In the southern reaches of our Milky Way, regions lying below the plane where the Sun and planets orbit, huge gravitational tides are slowly and silently rearranging how stars drift, how entire streams of gas twist, and even how the Milky Way itself bends. These cosmic tides are not quick like the rise and fall of the ocean. They take tens of millions, sometimes even billions of years, yet their influence is enormous. They stretch the galactic disk, ripple the stars like waves in a lake, and might even play a hidden role in shaping the history of life on Earth. It is easy to picture our galaxy as a flat, stable disk, like a record lying on a turntable, spinning calmly in space. But this image is misleading. The Milky Way is restless, shifting, and alive with motion. The disk ripples, twists, and warps in response to constant gravitational nudges, both from inside and outside. Imagine a great sheet of water spread across a pond. Drop a stone into it, and ripples spread out in circles. Now imagine that stone is not a single pebble but an entire small galaxy colliding with ours. The ripples from such an event spread across tens of thousands of light years, bending stars, dust, and even invisible clouds of dark matter. This is exactly what has been happening as the Milky Way interacts with smaller companion galaxies that orbit around it. One of the greatest influences comes from a satellite galaxy with a poetic name, the Sagittarius dwarf spheroidal galaxy. Though it is small compared to the Milky Way, it has had an outsized effect. Like a moth circling a flame, Sagittarius orbits in a tilted, stretched-out path that cuts right through the Milky Way's disk. Every time it plunges through, it shakes the disk, leaving behind ripples of stars and streams of debris. These ripples are not gentle. They are strong enough to stretch the southern half of the galaxy, tugging at the orbits of stars, including our own Sun. Even the elusive dark matter halo, which scientists believe surrounds the Milky Way, is pulled and reshaped by this ongoing collision. In many ways, Sagittarius is not simply orbiting, it is being devoured. The Milky Way is tearing it apart piece by piece, swallowing its stars and scattering them across the galactic disk. Long streams of Sagittarius stars now arc through the sky, a ghostly record of its slow destruction. But in dying, Sagittarius is also reshaping its killer. Sagittarius is not alone in influencing the Milky Way. Two other companions, the Large Magellanic Cloud and the Small Magellanic Cloud, play their own part. These galaxies orbit below the southern edge of the Milky Way's disk. Though smaller than our galaxy, They are massive enough to drag at it. Their combined gravity pulls at the Milky Way's outer regions, bending its ring of stars and gas. Picture a ship moving across the ocean. As it cuts through the water, it leaves behind a wake, a V-shaped pattern of waves trailing in its path. The Magellanic Clouds do something similar, but with stars and dark matter instead of seawater. As they orbit, they drag along part of the Milky Way's unseen halo, creating a gravitational wake. This invisible current tugs on stars and clouds of gas, creating vertical waves that ripple through the galactic disk. Scientists have a name for this trembling of the galaxy: galactic seismology. Just as seismologists study earthquakes to understand the inner structure of Earth, astronomers study these galactic ripples to learn how the Milky Way is built. For centuries, astronomers could only guess at these movements. Stars seemed fixed in the sky, their motions too small to see with the naked eye. But now, thanks to the Gaia satellite launched by the European Space Agency, we have a new view. Gaia is like a cosmic cartographer, carefully measuring the positions and motions of over 1 billion stars. With this vast dataset, astronomers can see the Milky Way as a living, moving system rather than a frozen picture. What Gaia has revealed is breathtaking. The ripples in the galactic disk are not just small quirks, they rise and fall across thousands of light years. The entire galaxy is vibrating in slow motion, responding to ancient impacts from Sagittarius, the Magellanic Clouds, and perhaps other long-lost satellites. These ripples stretch vertically above and below the galactic plane, proving that the Milky Way is not flat at all, but a warped, breathing structure. We might feel distant from these cosmic tides, safe on our small planet. Yet Earth itself is not exempt. The Sun, along with the entire solar system, is drifting in this galactic sea. As it orbits around the Milky Way once every 225 million years, it does not move in a perfect circle. Instead, it bobs up and down through the galactic plane like a cork riding waves. This vertical motion takes about 60 to 70 million years for a single cycle. Some researchers believe these oscillations could have consequences for life on Earth. When the solar system passes through denser regions of the galactic plane, it may encounter more cosmic dust or experience gravitational nudges that send comets hurtling toward the inner solar system. Such increases in comet activity could cause mass extinctions, leaving scars in Earth's fossil record. Though the evidence is debated, the possibility is tantalizing. The tides of the galaxy may not only shape stars and gas, but also influence the history of life itself. Imagine entire epochs of evolution, dinosaurs rising, thriving, and falling, linked, at least in part, to the slow, steady rhythm of the solar system's galactic journey. One of the most striking discoveries about these galactic tides is that they affect the northern and southern halves of the Milky Way differently. The southern part of the disk, the side where the Sagittarius galaxy plunges and the Magellanic Clouds orbit, shows stronger warps and ripples. It bends more sharply, pulled by these companions below. The northern side is calmer but not untouched. It too feels the tug, but the asymmetry reveals how uneven gravity can be across a structure as enormous as a galaxy. These differences hint that the Milky Way's very shape is still being moulded. Far from being a settled structure, the galaxy is a work in progress, reshaped by interactions and tides, stretching over billions of years. It is not just stars that are shifted by these tides. Clouds of gas, the raw material for future stars, are rippled and stretched. Even more mysterious, the dark matter halo surrounding the Milky Way feels the tug. Though invisible, dark matter makes up most of the galaxy's mass. Its clumping and stretching influence how stars move and how galaxies evolve. By studying how tidal forces shift dark matter, scientists hope to learn more about its nature. Is dark matter made of weakly interacting particles, vast invisible clouds, or something stranger still? The tides may hold clues. Every ripple in the galactic disk is also a fingerprint left on dark matter, waiting to be read. Astronomers often speak of exploring the frontier, but usually they mean the outer edges of the galaxy, or the farthest observable galaxies in the universe. Yet there is another frontier right beneath us, the vertical space below the galactic plane. This region, influenced by tides, is full of hidden structures, streams of stars torn from Sagittarius, rippling waves stirred by the Magellanic Clouds, and unseen concentrations of dark matter. The frontier is invisible to the naked eye, yet Gaia and other instruments are beginning to reveal it. It is here, in these vertical depths, that the next great discoveries in astrophysics may await. Step back for a moment and see the bigger picture. We live not on a still, calm island, but within a galaxy alive with motion. The Sun and Earth are passengers in a ship that rocks and sways through tides stretching across light years. Our planet's history, its oceans, mountains, and living creatures, may carry the imprint of these galactic rhythms. The story of tides, then, is much larger than the daily rise and fall of the sea. It is the story of gravity weaving patterns across space and time. From the moon pulling on Earth's waters, to black holes tearing at stars, to entire galaxies rippling like ponds, tides remind us that nothing in the universe is fixed. Everything bends, shifts and dances to gravity's tune. The southern half of the Milky Way, tugged and warped by its companions, is not just a backdrop for stars. It is a living frontier, full of mysteries still unfolding. These tides cluster dark matter, ripple gas clouds, shift the paths of stars and even nudge the solar system itself. Far from being empty, the space below the galactic plane is a realm of hidden forces. It holds ghostly streams of devoured galaxies, wakes left by satellite companions, and vibrations recorded in the stars themselves. It is a place where we can see the fingerprints of gravity's invisible hand. Deep beneath the smooth, round path that our solar system follows around the Milky Way lies something huge, ancient, and impossible to miss: the galactic center. This is the true heart of our galaxy, the gravity anchor that keeps everything together. It is not an empty place, and it is not quiet. Instead, it is a restless, crowded, glowing, and often violent area where countless stars burn, where magnetic fields twist and tangle like invisible ropes, and where, at the very center, hides a giant black hole called Sagittarius A star. Our solar system is not sitting still inside the Milky Way. Like a tiny speck caught in a whirlpool, it moves along with the rest of the galactic disk, circling the center in a wide, nearly flat path. One complete trip around the galaxy takes an unbelievably long time, about 225 million years. That means the last time we were in the same spot in our orbit, dinosaurs were walking on Earth. But our solar system's path is not perfectly smooth or flat. Gravity never allows such neatness. Instead, the solar system bobs gently up and down as it moves, the way a ship rises and falls on the waves of an ocean. Astronomers have found that this up and down motion happens on a cycle of about 30 to 35 million years. Every so often we cross the thin middle layer of the Milky Way, rise high above it, and then sink back down again, pulled by the combined tug of stars, gas clouds, and even the strange unseen stuff we call dark matter. Right now, our solar system sits about 25 to 30 light years above the galaxy's middle layer. We are slowly drifting downward, so gently that no person could ever feel it in a single lifetime. And yet this up and down movement is not without meaning. It plays an important role in how matter flows through the galaxy. Gas, dust, and even whole star systems can drift above and below the disk, slowly sliding toward the center in ways that astronomers are only beginning to uncover. Picture for a moment that you could drop an object from our solar system's current spot and simply let it fall downward toward the center of the galaxy. At first, it would pass through the galactic disk itself, the wide, flat region where most of the stars, glowing clouds, and rivers of dust are found. This is the Milky Way as we see it stretched across the night sky, a shining band filled with so many suns that their light melts together into a misty glow. As the falling object goes deeper, the pull of gravity grows ever stronger. The closer it moves towards Sagittarius A star, the more the invisible grip of gravity tightens. Our Sun lies about 26,000 light-years away from the galactic center, so the object would have an extremely long way to fall. Each passing light-year would make it faster. Space and time itself, the very fabric of reality, bend inward, steepening the fall as though the object were sliding down a giant invisible funnel. This imagined drop would never be simple or straight. The Milky Way is not a calm pond. It spins, and like a whirlpool, its inner regions spin faster than the outer edges. Anything falling inward from above or below would be caught in that spin. Instead of rushing straight to the centre, the object would spiral, trapped in the swirling dance of the galaxy's arms. Its path would carry it through areas far thicker than anything near Earth, regions where stars are packed so tightly that the night sky would blaze like a box of jewels. The spiral fall would carry it through the galactic bulge, a thick rounded cloud of old stars that glow red with age. Here, stars can be hundreds of times more crowded than in our quiet neighbourhood near the Sun. Along the way, the object would pass through giant gas clouds, cold and dark where new stars are slowly forming. It would weave through magnetic strands, unseen but powerful, and enter the wild chaos of the central zone, where stars are born and die side by side in a never-ending cycle of creation and destruction. One especially interesting part of imagining a fall from beneath the galactic disk is that the southern half of our galaxy, the sky below the disk, has long been less explored than the northern half. For centuries, most of the world's big observatories were built in the northern hemisphere, which meant astronomers had a clearer view of the stars above the disk than those below it. That is now changing. New telescopes in the southern hemisphere, such as the Vista telescope in Chile, have started mapping the hidden southern skies. Soon, the powerful Vera C. Rubin Observatory will join them, giving us breathtakingly detailed pictures of areas we have only glimpsed until now. For the first time in human history, we will be able to study the southern path of this imagined fall toward the galactic centre with the same detail as the north. As the object goes further, it would pass through stranger and harsher regions. Matter and radiation become denser. Magnetic fields twist tighter and snarl into wild shapes. Neutron stars, the collapsed leftovers of massive suns, hide like embers of cosmic violence. Stars crash into each other, and smaller black holes drift unseen, each a hidden trap in the dark. And finally, at the centre of it all sits Sagittarius A star, a giant black hole with a mass of about 4,300,000 suns. Almost still, it anchors the galaxy with its enormous pull, shaping the paths of stars even tens of thousands of light years away. To come near it is to enter a place where light itself bends, where time slows, and where space takes on strange shapes. Although Sagittarius A star is fairly quiet now, marks in the sky show it was not always so calm. Astronomers have found proof that a few million years ago it exploded in huge bursts, blasting streams of energy far into space. The leftovers of those blasts remain today as two giant bubble-shaped structures, the Fermi bubbles, that rise high above and below the galactic plane. They are silent reminders of the black hole's once fiery past. Close to the black hole lies the innermost safe circular orbit, a kind of invisible edge. Any object spiralling inward that crosses this line can no longer resist. It cannot stay in orbit. It falls. Yet in truth, most objects never make it that far. Long before reaching this edge, they are torn apart by tidal forces, burned by radiation, or ripped apart by magnetic storms. This thought experiment is not just poetic imagination. Astronomers take the idea of falling toward the galactic centre very seriously. The up and down motions of stars and gas, their rising and sinking above and below the galactic disk, are key to understanding how the Milky Way changes over billions of years. These motions explain how stars drift to new areas, how gas clouds spread or collapse, and how, over time, matter is drawn toward the black hole at the centre. When enough matter gathers near Sagittarius A star, it can cause new blasts of energy, huge events powerful enough to reshape the galaxy itself. In this way, the Milky Way is not a calm, flat pinwheel of stars circling forever in neat paths. It is a living, restless system where matter constantly collides, drifts, and sometimes plunges straight into the heart of darkness. This same story of rising, falling, and spiralling inward can be seen on a much smaller scale right here in our solar system. Around the planets is a thick cloud of dust that lies mostly along the flat orbital path called the ecliptic. For a long time, astronomers thought this dust was limited to a single thin layer, but thanks to powerful infrared space telescopes such as IRIS and COBE, we now know that the dust forms many layers, some stretching far above and below the main plane. The dust is slowly pulled inward by the sun's gravity, but the planets also shape its spread with their own gravity. On top of that, a gentle effect known as Poynting-Robertson drag makes the dust spiral inward, closer and closer to the sun, like grains of sand sliding down a whirlpool. Along the way, many of these dust bits cross Earth's path, sometimes from above the orbital plane, sometimes from below. Even more surprising is that not all of these dust grains were born here. Some are interstellar micrometeoroids, tiny pieces of matter that come from outside our solar system. These wanderers rush in on sharp paths, entering the solar bubble from all directions. Readings from spacecraft such as Ulysses, Galileo, and Cassini show that a large part of this incoming dust comes from the direction of the galactic south, slicing through our system from below the planetary plane. These interstellar grains are unbelievably small and fast, so tiny that they are almost invisible, yet so quick that they hit with huge force. Most are too small to punch holes in spacecraft, but over long stretches of time they can cause real damage. They scratch protective blankets, blur lenses, and sometimes pierce fragile solar panels. The International Space Station takes this threat very seriously. Its modules are wrapped in shielding, and its position is carefully adjusted to lower exposure during meteor showers. The smallest dust grains may not look like much, but when you're moving at orbital speeds, even a speck can hit like a bullet. To study and predict these hits, scientists use advanced tools such as DRAGONS, short for Debris-Resistive Acoustic Grid Orbital Navy Sensor. This device can detect dust hits in real time, helping researchers map the angles and speeds of incoming micrometeoroids. Many of these readings confirm that a large portion of them do indeed come from the southern sky, striking from beneath Earth's orbital plane. Future missions will face even bigger challenges. Spacecraft like Solar Orbiter, which already travels outside the main planetary plane, are beginning to sample dust in unusual paths. More daring missions that head toward the far-off Oort cloud, the icy shell at the edge of our solar system, will meet micrometeoroids unlike any seen near the inner planets. Studying these grains, especially those that come in from unusual angles, is teaching us that our solar system is not a neat flat pancake of planets circling the sun. Instead, it is a three-dimensional, always shifting stage where dust and debris float, crash, fall inward, and reshape the cosmic space around us. Most of us, when we stop to imagine the universe, think first of the familiar scenes often shown in books, movies, and classroom posters. We picture planets spinning gracefully in wide circular paths around the sun, each one locked in its orbit as if tied by invisible strings. We imagine comets with long glowing tails, sweeping across the heavens on their stretched out journeys that take them close to the sun before flinging them far into the cold outer reaches of space. We feel comfort in thinking of the sun as the steady anchor at the centre, its gravity holding everything together like a conductor keeping an orchestra in perfect time. This picture gives us a sense of harmony. Planets move in reliable paths, orbits follow clear rules, and gravity quietly keeps the cosmic music going without fail. But beneath this simple picture lies something far stranger, something hidden, delicate, and far more fascinating than we might first guess. Astronomers and mathematicians, through decades of patient work, are starting to reveal what might be called the secret architecture of the universe. This structure is not made of bricks or beams. It is not carved into stone or stitched into cloth. Instead, it is woven into the very fabric of space through the gentle yet relentless pull of gravity. This hidden structure is made up of what could be described as gravitational corridors or cosmic highways. They are invisible lanes that exist all around us, threading through the solar system and beyond. These corridors are not tunnels we could ever enter physically, and no telescope, no matter how powerful, could show them as glowing streaks across the sky. They exist in a subtler way, etched into space itself, created by the combined gravity of the Sun, the planets, and even the greater body of our Milky Way galaxy. Imagine them as natural pathways through the void, lanes where objects can travel with very little effort, as though sliding along a hidden river. To picture them, think of how water flows across a landscape. A river does not forcefully cut its way across the land all at once. Instead, over time, it follows the gentle slope of valleys, always finding the easiest path downhill. In the same way, these gravitational lanes guide the movements of comets, asteroids, spacecraft, and even drifting dust. They are like riverbeds carved not from soil or stone but from the subtle balance of gravitational forces. For centuries, scientists believed that all the real action of gravity happened mostly on a flat stage, the ecliptic plane, the thin disc-like region where the planets move around the Sun. It was in this plane that astronomers discovered something remarkable, a system of invisible routes known as the Interplanetary Transport Network. This network is shaped by Lagrange points, named after the mathematician Joseph Louis Lagrange, who described them in the 18th century. These are special spots in space where the pull of the Sun and a planet balance each other out. Imagine two children on a seesaw. At certain places, a ball placed between them will not roll toward either child. It will just sit balanced. In space, such balancing spots become gateways. At these points, spacecraft, comets, or even loose rocks can hover, drift slowly, or move in looping paths that seem chaotic but are still controlled. They are like quiet harbours or crossroads in the sea of space. When connected together, these Lagrange points create webs of motion, a set of interlinked routes that make travel between planets easier. Engineers have already used these routes to save fuel on real missions, allowing spacecraft to drift from one world to another with far less effort than would otherwise be required. For the longest time, humanity's gaze stayed fixed on this thin, flat sheet of orbits. It was natural. We saw the solar system like a table, and everything important seemed to sit neatly upon it. But what happens if we tilt our view? What if instead of looking only at the flat disk, we explore the hidden dimensions above and below? In recent decades, mathematicians and astronomers have dared to do just that. They turned to a famous puzzle in celestial mechanics known as the restricted three-body problem. This problem asks, what happens when three objects, say, the Sun, a massive planet like Jupiter, and a much smaller traveller like an asteroid or a spacecraft, interact with one another's gravity? The answer revealed something profound. Gravity is not flat. It does not simply form a smooth sheet across space. Instead, it folds, bends, and curves in all directions, creating a three-dimensional landscape. Imagine a map not made of hills and valleys of stone, but of pure gravitational energy. This landscape is filled with slopes, ridges, basins, and mountain passes. It is through these invisible features that secret routes open, not only across the flat planetary plane, but also above it and far below it. In these higher and lower regions, gravity creates valleys that act like downhill slopes. Just as water naturally flows into valleys, objects in space tend to slide into these gravitational channels. A spacecraft, if guided carefully into one of these lanes, could travel vast distances with very little fuel. It would be as though the ship were floating downstream on a gentle current, with nature itself providing the push. This is not only theory. In fact, space agencies have already begun to take advantage of these hidden lanes. NASA's Lucy mission, launched to study the Trojan asteroids near Jupiter, and the European Space Agency's JUICE mission, which is exploring Jupiter's icy moons, both rely on these natural highways. Instead of wasting fuel fighting against gravity, these spacecraft surf along the curves and slopes of space, turning a complex dance into a graceful glide. One of the most intriguing possibilities is that these gravitational corridors may not only stretch outward, but also funnel inward, diving beneath the Sun's pull in areas where the influence of the planets is weaker. In such regions, gravity's lanes may act like channels guiding asteroids, comets, and even interstellar fragments toward the center of the solar system. Imagine an icy body drifting far away at the edge of the Sun's domain, perhaps in the mysterious Oort cloud, which lies nearly 1 light-year away. Instead of tumbling in randomly, such an object might slide inward along one of these hidden paths, drawn gently like a leaf carried by a calm stream. This would explain why some comets appear in surprisingly neat trajectories, as if they were guided by invisible hands. At the heart of this entire system is the Sun. Its immense weight bends space itself, curving the very structure of reality. But the Sun is not alone. The whole Milky Way also plays its part. The galaxy has a dense midplane, a flat sheet filled with stars, gas, and dust. The combined pull of the Sun and this galactic midplane creates an even grander design, gradients and slopes that open natural routes upward, downward, inward, and outward. Picture a spacecraft positioned beneath the Sun, aligned with one of these gravitational channels. With just the smallest push, it could ride the natural escape slope and be flung outward from the solar system, sailing gracefully into the southern skies and beyond toward distant stars and galaxies. What seems like magic is only the careful use of gravity's quiet architecture. These hidden lanes may not just be useful tools for the future, they may also have played a critical role in the past. Billions of years ago, when the solar system was still young and taking shape, countless icy rocks and small building blocks of planets were scattered across the outer disk. Many of them may have rained downward through these gravitational funnels, delivering water, ice, and essential minerals to the forming inner planets. This slow but steady delivery of material could explain why Earth has oceans, why Mars once had flowing rivers, and why the mixtures of elements on some planets appear uneven. The unusual tilts of some worlds may even be fingerprints of this ancient vertical infall, where streams of debris from above or below helped shape the very architecture of our planetary family. But these corridors are not always smooth highways. Sometimes they act as traps. A small piece of rock, a drifting cloud of dust, or even a fragment of human-made spacecraft can fall into one of these pathways and become caught in an unusual orbit. Such objects may circle the Sun in tilted, looping, or chaotic paths, held in place for years or even for billions of years by gravity's patient hand. This may explain why astronomers occasionally discover strange groups of rocks travelling together, or mysterious clouds of dust hovering in tilted positions. Some of these trapped wanderers could be as old as the solar system itself, quietly drifting in hidden orbits while the planets move along their well-known tracks. Understanding these gravitational lanes is not just a matter of satisfying curiosity, it may be vital for the future of space exploration. Missions to the distant Kuiper Belt, journeys into true interstellar space, or even strategies to push dangerous asteroids away from Earth could all depend on our ability to map and use these hidden highways. Instead of wasting enormous amounts of fuel, humanity could one day learn to move through the solar system with elegance and efficiency, gliding as naturally as a bird riding the wind or a fish drifting with the ocean's current. And if we can imagine this, perhaps other civilizations have already discovered it. If intelligent beings exist elsewhere among the stars, they may have long ago mastered the art of using gravitational corridors. Instead of building massive engines, they could be slipping silently along these invisible trade winds of space, travelling between star systems the way ancient sailors once followed ocean currents across Earth. Perhaps the universe is already threaded with such ancient routes, invisible to most but patiently waiting for us to recognise them. Our spacecraft may one day follow in the wake of others who came before, gliding quietly along the timeless roads carved by gravity. Far above the shining star-filled band of our Milky Way galaxy, and equally far below its crowded heart, rise two of the most astonishing and mysterious structures that human beings have ever discovered in the universe. These vast shapes are not like stars or planets, nor are they like the graceful spirals of dust that swirl across the galaxy. Instead, they are strange, glowing towers of energy so immense that they seem almost unreal. Astronomers call them the Fermi bubbles, two gigantic balloon-like forms that stretch tens of thousands of light-years into space, filled with invisible light of the most powerful kind. They are not gentle clouds or soft halos. They burn with an energy so fierce that they slice across the galaxy like deep scars carved into the heavens themselves. From Earth, human eyes cannot see them at all, for they shine not with ordinary light but with the blazing power of gamma rays, the strongest and most energetic kind of light known in the universe. The bubbles were first revealed in the year 2010, when NASA's Fermi Gamma Ray Space Telescope turned its gaze toward the central regions of the Milky Way. The telescope picked up two ghostly symmetrical towers stretching above and below the galactic plane, glowing faintly but unmistakably in gamma rays. Their discovery shook astronomers, because no one had expected to find such structures hanging over the galaxy like cosmic lanterns. From that moment forward, the Fermi bubbles became one of the greatest mysteries in modern astronomy. Two colossal beacons daring scientists to uncover their origin. To understand the scale of these structures, one must picture the galaxy itself. The Milky Way is a giant spiral of stars, gas, and dark matter, about 100,000 light-years across from side to side. At its centre lies a bulging core crowded with stars and hidden by clouds of dust. Surrounding this disk and bulge is a faint halo of stars and invisible matter that extends much farther outward. Now imagine, rising straight above and below this galactic disk, two enormous lobes. Each one stretches about 25,000 light-years into space. To compare, that is roughly the same distance between our Earth and the very core of the Milky Way itself. Put differently, if you could travel from our solar system to the centre of the galaxy, you would cover about the same distance as the height of just one of these bubbles. And there are two of them, one reaching upward, one downward, balanced perfectly on either side of the galaxy's shining midplane. Seen together, they give the impression of some great cosmic sculpture, as though an unimaginably powerful hand had carved two symmetrical cavities into the fabric of the galaxy, filling them with energy and light. What makes the Fermi bubbles truly remarkable is not only their sheer size, but also their content. They are flooded with gamma rays, the most energetic kind of radiation in the cosmos. Gamma rays are very different from the familiar forms of light that human beings encounter in daily life. The warm glow of infrared light, the brightness of visible sunlight, and even the sharp beams of X-rays used in hospitals. All of these are weak compared to the staggering intensity of gamma rays. These rays carry energies millions or even billions of times higher than visible light, and unlike ordinary light, gamma rays are born only in the most extreme and violent places in the universe. They appear when stars explode in supernova, when black holes rip matter apart as it falls into their gravity, or when particles slam into one another at nearly the speed of light. They are the signatures of cosmic violence, the fingerprints of titanic forces. That is the energy filling the Fermi bubbles. Imagine two balloons, each the size of a quarter of the galaxy, swollen not with air but with the fiercest light known to science. Another astonishing feature of the bubbles is how sharply defined they are. Many structures in astronomy, nebulae, halos, clouds of gas, fade gently into the background of space, blurring at their edges. But not the Fermi bubbles. They have crisp, almost blade-like boundaries, as if their surfaces were carved with a razor of cosmic energy. They do not blend softly into the galaxy's background haze. Instead, they appear like two towers of light that pierce straight into the galactic halo. The halo itself is an enormous, ghostly region surrounding the Milky Way, filled with thin gas, faint stars, and the mysterious dark matter that holds the galaxy together. The bubbles rise into this space like monumental pillars, pressing against the halo gas, squeezing it and heating it. Inside the bubbles, astronomers have detected plasma heated to extreme temperatures, high-energy particles racing at unimaginable speeds, and magnetic fields twisted into tangled shapes. Even more incredible, the bubbles seem to be expanding, pushing outward into space at nearly 1,000 kilometers per second. That means that in the time it takes for a human heart to beat once, the edge of a bubble swells outward by hundreds of kilometers. No human machine could ever approach such speed. It is pure galactic power at work. Yet with all their size, brightness, and sharp definition, the bubbles pose a riddle. What made them? When astronomers first examined them, they searched for obvious causes. Perhaps, they thought, a cluster of supernova explosions had gone off in the galactic center, hurling matter and energy outward. Or perhaps a region of intense star formation had driven winds powerful enough to carve out the bubbles, but no such nearby event was found. There was no evidence of a massive starburst or of a chain of supernovae strong enough to explain such enormous structures. The puzzle forced scientists to look deeper, to consider the most powerful engine known in the galaxy, the supermassive black hole at its very core. At the center of the Milky Way lies Sagittarius A star, a black hole weighing about 4 million times the mass of our Sun. Today, it is relatively quiet, lurking silently, nibbling occasionally on stray clouds of gas. But black holes are known to have tempers. In other galaxies, astronomers have seen black holes devour matter in great feasts, blasting out colossal jets of particles and radiation in the process. What if, millions of years ago, Sagittarius A star had such an outburst? Imagine the black hole swallowing vast clouds of gas, becoming active, and spewing out twin jets of particles upward and downward from the galactic plane. These jets would have carved their way into the halo, heating the gas, twisting magnetic fields, and filling the sky with gamma rays. Over time, the jets would have slowed, faded, and spread into the balloon-like shapes we now see as the Fermi bubbles. In this view, the bubbles are the fossils of a black hole's tantrum, glowing reminders of a long-ago eruption at the galaxy's heart. But not all scientists agree. There is another possible story. Perhaps the bubbles were not born from the fury of the central black hole at all. Perhaps they were sculpted by a starburst event, a time when stars were born in an overwhelming rush near the galactic centre. In certain conditions, clouds of gas can collapse so quickly that thousands or even millions of stars form within a relatively short cosmic time. Such frenzies of star formation release tremendous amounts of energy. Young stars produce fierce winds of gas and radiation. Some of them quickly explode as supernovae, adding their blast to the storm. Together, these forces can push material outward from the galaxy's heart in massive flows. Such starburst winds could easily carve bubbles into the halo, pushing out hot plasma and leaving behind giant lobes filled with radiation. If this is true, then the Fermi bubbles are monuments not to a black hole's rage, but to a storm of newborn stars long since gone quiet. Whichever story is true, the result is the same. Two enormous lobes of energy, glowing faintly after millions of years, standing as silent reminders of a forgotten catastrophe in the Milky Way's past. And the bubbles are not simple in their design. Within them, astronomers have found layers of energy. Observatories such as Rosat and Erosita, which detect X-rays, have revealed glowing regions inside the bubbles. Along the edges, sharp boundaries appear, resembling shock fronts. These are like cosmic versions of the ripples created when a boat slices through water, pressure waves marking the boundaries where the bubbles push against the thin halo gas. Even more fascinating, the bubbles may be unstable. Some studies suggest that they are not perfectly steady structures, but are shifting, swelling, or fading over time, depending on how the pressure inside them struggles against the surrounding halo. Their symmetry, however, points directly back to the galaxy's core, leaving little doubt that their birth came from deep within. This raises another question. Is the Milky Way unique in having such bubbles, or are they part of a larger galactic pattern? The evidence suggests the latter. Other galaxies show similar structures. For instance, the galaxy known as Centaurus A displays giant lobes of radio energy extending outward from its centre, much like the Fermi bubbles. These examples hint that such eruptions are not rare accidents, but may be a natural stage in the life of spiral galaxies. Perhaps galaxies occasionally flare with energy from their cores, whether through black hole eruptions or starburst winds, leaving behind glowing bubbles that linger for millions of years. From Earth, no stargazer can ever see the Fermi bubbles with the naked eye. They are invisible to ordinary sight, hidden from human vision because our eyes cannot detect gamma rays. To us, the night sky appears full of stars, constellations, and the hazy band of the Milky Way. But through the eyes of a gamma-ray telescope, the sky transforms. The familiar constellations vanish, drowned in the overwhelming glow of the bubbles. Instead of Orion, the Scorpion, or the Great Bear, one would see two colossal pillars of light stretching above and below the Milky Way's shining disk. They would look like monuments carved into the heavens, ancient towers standing as reminders of the forces that once shook the heart of the galaxy. Far below the familiar stage on which our solar system drifts, beneath the great disk of the Milky Way with its swirling lanes of stars, gas and dust, lies something far more peculiar than a drifting comet or a faint nebula. It is not a loose cloud of particles, nor a wandering star that has lost its way. Instead, it is something much deeper, something written into the very fabric of space itself. It is like a scar, an icy bruise, a wound etched not in matter, but in light. And not just any light. This mark is imprinted on the oldest light that human eyes have ever glimpsed, the dim echo of the universe's birth. This peculiar mark is found in what astronomers call the cosmic microwave background radiation, often shortened to CMB. To understand it, imagine the universe as a grand stage play that began nearly 14 billion years ago, when the Big Bang, the enormous burst that created both space and time, set everything into motion. The CMB is the fading afterglow of that beginning. It is the soft echo left behind, like embers cooling after a fire, or like the fading glow of a sunset that lingers long after the sun itself has dropped below the horizon. If we look at the sky with our normal eyes, tuned to visible light, we see the stars scattered like diamonds on black velvet. We see galaxies and the colourful fogs of nebulae. But if we could switch our vision into microwave light, much longer waves of energy that are invisible to us, we would discover something astonishing. we would see that the entire sky, in every direction, is covered by a faint, even glow. It is as if someone painted the heavens with a dull, uniform brush. This is the CMB, the afterimage of creation. But here is the strange part. This glow, while almost uniform, is not perfectly smooth. Hidden within it are tiny ripples, patches that are a little warmer and patches that are a little cooler. The differences are incredibly small, only millionths of a degree, yet these minute variations are cosmic treasure. They are the fingerprints of the early universe, the tiny seeds that later grew into all the grand structures we know, galaxies, stars, planets, and even ourselves. Without these delicate ripples, the universe would have remained an endless soup of gas, with no stars ever lighting up the darkness. Among these delicate ripples lies something that has puzzled scientists for decades, a single region, far larger and stranger than the rest. It is not just a subtle variation, it is a great hollow, a cold scar in the otherwise gentle glow. Astronomers call it the cosmic microwave background cold spot, or simply the cold spot. The cold spot rests in a southern constellation named Eridanus, a long winding river of stars. It lies well below the Sun's ecliptic path, the invisible line that traces the Sun's yearly journey across our sky, and even deeper beneath the central plane of the Milky Way. This makes it part of the great southern sky, a region less familiar to many people in the northern hemisphere but rich in myth, history, and cosmic mystery. The cold spot is not small. It spans nearly 5 degrees across the heavens. To understand how vast that is, think of the full moon. Hold it up in the night sky, and now imagine a patch of sky 10 times as wide. That is the size of this cold bruise in the cosmic background, an enormous region compared to most of the tiny ripples that cover the CMB map. What truly sets the cold spot apart is its temperature. It is about 70 microkelvin colder than the average surrounding glow. A microkelvin is a millionth of a degree. To our everyday lives, this sounds almost laughable. 70 millionths of a degree colder? That would not even chill a glass of water. Yet in the precise field of cosmology, where scientists study the tiniest differences in ancient light, this is no small thing. This is a shiver that cuts across the entire universe, a subtle but powerful chill that cannot easily be ignored. To scientists, this 70 microkelvin drop is like a whisper out of tune in a grand orchestra. Everything else fits within the expected harmonies of cosmic history, but this one region plays a strange and unexpected note. Hints of this anomaly first appeared in the year 2004. That was when NASA's Wilkinson Microwave Anisotropy Probe, or WMAP, produced a detailed map of the cosmic microwave background. For the first time, humanity had a clear and precise picture of the faint afterglow of creation. The map revealed the expected tiny ripples, but in the southern sky, WMAP also revealed something far more dramatic: the cold spot. Nearly a decade later, in the year 2013, another space mission took up the task. The European Space Agency's Planck satellite was designed to measure the CMB with even greater accuracy than WMAP. When Planck turned its eyes to the same region, the result was undeniable. The cold spot was real. It was not a trick of the instruments or an illusion in the data. It was there, stubbornly imprinted on the cosmic background itself. Both missions had been created to measure the faint glow of the early universe with extreme care. Both told the same story. The cold spot is too large, too deep, and too improbable to be dismissed as random noise. Normally, scientists expect fluctuations in the CMB. In fact, these fluctuations are essential. Without them, the universe would never have formed galaxies, stars, or planets. But the cold spot is no ordinary fluctuation. It is a giant among ripples, a deep hollow in a gentle sea. Its very existence challenges the neat story of the early universe. Statistically, the odds of such a large feature appearing by chance are extraordinarily small. That makes it one of the great puzzles of modern cosmology. Adding to the mystery is its location. The cold spot lies in the southern galactic hemisphere, an area of the sky relatively free from interference. There is less cosmic dust there, less stray radiation from the Milky Way, and fewer local sources that might distort the signal. That means the cold spot cannot easily be blamed on contamination. Its presence must be explained by something deeper. So what could cause such a strange chill in the fabric of the cosmos? Scientists have suggested several possibilities, ranging from the simple to the breathtaking. The simplest explanation is that the cold spot is just a statistical fluke. Perhaps during the turbulent froth of the early universe, one quantum fluctuation simply grew much larger than usual, leaving behind this unusual cold mark. Mathematically, this is possible. The laws of probability allow for rare and unlikely events, but emotionally and scientifically, many researchers find this explanation unsatisfying. The odds are so slim that it feels like the universe's most improbable lottery win. Another possibility is more dramatic. Perhaps the cold spot is the result of a supervoid, a gigantic region of the universe almost empty of galaxies. Imagine a cosmic desert stretching hundreds of millions of light-years across, with only a sparse sprinkling of galaxies. If photons from the CMB had to pass through such a region on their way to Earth, they would lose a little energy. This energy loss, caused by something called the integrated Sachs-Wolf effect, would make them arrive colder than expected. Indeed, galaxy surveys have found evidence for a large underdense region in the direction of the cold spot. But here lies the problem. The void is not empty enough. It is large, yes, but not nearly empty enough to account for the 70 microkelvin drop. It explains part of the mystery, but not the whole. The most exciting possibility is also the boldest. Some scientists wonder if the cold spot might be the scar of a cosmic collision. During the earliest moments after the Big Bang, the universe is thought to have undergone a phase called inflation, when it expanded faster than the speed of light. If our universe is only one bubble in a greater multiverse, then perhaps during inflation, our bubble brushed against another. The cold spot might be the bruise left behind from that ancient clash. If true, this would mean the cold spot is not only a clue about the early universe, but also a hint that we are not alone, that our cosmos is just one among countless others. So far, no firm evidence proves this breathtaking theory. Yet its very possibility makes the cold spot one of the most tantalizing mysteries in science. The cold spot is not entirely alone. Astronomers have noticed that several other unusual features of the CMB also seem to favour the southern sky. Large-scale patterns show odd alignments, statistical imbalances between northern and southern hemispheres, and what some researchers jokingly call the axis of evil. These features remain controversial. Some scientists argue they are artifacts of observation, quirks of measurement or calibration. But repeated tests with different satellites and different instruments continue to show the same thing. The anomalies are stubbornly real. And here is something even more fascinating. The area around the cold spot is one of the cleanest windows into the CMB in the whole sky. There is little dust, little interference, and very little background noise. That makes the cold spot like a pristine laboratory, a natural experiment carved into the universe itself. Every unusual result here matters more, because there is nothing obvious to blame it on. Today, nearly 2 decades after its discovery, the cold spot remains one of the most puzzling features of the cosmos. It is invisible to our eyes, a shadow written not in stars but in ancient light. It does not sparkle or shine. It does not call attention to itself in any ordinary way. Yet it whispers through every attempt we make to understand the universe's beginnings. Some scientists shrug and call it a statistical oddity. Others argue it is the fingerprint of a supervoid. And a few dare to dream that it is the scar of another universe brushing against our own. Whatever it may be, the cold spot reminds us of something humbling. Even in a sky that seems mapped and measured, mysteries remain. And these mysteries may hold the key not only to where we came from, but also to whether our universe is truly alone. For centuries, astronomers have spoken of something called the Galactic North Pole, a direction in space that points away from the flat plane of our galaxy. Looking toward this pole gives us a clear, unobstructed view of the far-off universe. Because the North Pole opens such a clean window into deep space, it has drawn great attention throughout history, becoming a favourite place for scientists to explore ancient and distant galaxies. But the cosmos, like the Earth, is not one-sided. For every north, there is a south. Just as the galactic North Pole offers its view of the universe, its opposite, the galactic South Pole, holds its own unique perspective. To gaze toward the South Pole is to unlock another cosmic window, a mirror image to the north, one that allows us to balance our understanding of the Milky Way. Only by looking both above and below the galactic disk can we truly grasp the symmetry, or perhaps the asymmetry, of our home galaxy. The galactic South Pole is not an abstract idea, but a real and measurable point in the sky. It lies in the constellation known as Sculptor, a faint collection of stars first described in the 18th century by the French astronomer Nicolas Louis de Lacaille. Sculptor is not a dramatic or brilliant constellation. It does not leap out at the eye like Orion or the Southern Cross. But hidden within its quiet outline lies a pathway into some of the farthest regions of the visible universe. To picture its position, imagine the Milky Way as an enormous flat spinning disk, like a great celestial pinwheel. This disk holds billions of stars, swirling arms of gas, and flowing streams of cosmic dust. Rising from this vast disk are two poles, the north and the south. The galactic South Pole sits exactly 90 degrees beneath the plane of the galaxy, standing as the precise opposite of the North Pole within the system astronomers use to chart the Milky Way. Even though the North Pole is often celebrated in research papers, star maps, and scientific conferences, the South Pole is equally vital. Without it, astronomers would only see one half of the galaxy's great symmetry. By comparing what is seen in the north with what is seen in the south, scientists can test whether the Milky Way is balanced, whether its halo of stars and dark matter truly forms a perfect sphere, or whether one side has been stretched and reshaped by the long history of galactic encounters. From Earth, the galactic South Pole reveals itself most clearly in the skies of the Southern Hemisphere. People living in regions such as South America, Africa, and Australia enjoy the best views of it. Those living in the Northern Hemisphere, however, never see this pole. It never rises above their horizon. For half of humanity, the Southern Pole remains a treasure hidden from view, a cosmic secret seen only by those under southern skies. Much like its northern twin, the southern pole of the galaxy is an unusually quiet region of space. In astronomy, quiet does not mean silence, but rather emptiness. It means the area is free from the clutter of nearby stars, glowing clouds of gas, and heavy lanes of interstellar dust that so often block or dim our vision. The heart of this polar zone is remarkably empty. And for astronomers, emptiness is a gift. It offers a clear window into the universe beyond, into the greater structures that lie outside the Milky Way, colossal clusters of galaxies, delicate filaments of matter, and the wide dark voids that stretch between them. Because of this clarity, the galactic South Pole has long been a favourite hunting ground for astronomers who wish to chart the universe in 3 dimensions. One of the most famous projects based there was the 2-degree field galaxy redshift survey, often shortened to 2DFGRS. This massive project began in the late 20th century and continued into the early 21st century. Over the course of its work, it measured the distances to more than 200,000 galaxies. It was one of the most ambitious surveys of its time. Why was the galactic South Pole chosen for such a task? The reason is simple: its clarity. Because this portion of the sky holds little dust or gas, it experiences extremely low extinction, a term astronomers use to describe how light is dimmed or blocked by material inside the Milky Way. With so little interference, the view from this region is sharp, bright, and undistorted. It provides one of the cleanest cross-sections of the universe available, a priceless window into the structure of the cosmos. Through these surveys, scientists were able to create some of the very first large-scale maps of the cosmic web, the grand structure of the universe. These maps showed something astonishing. Galaxies are not spread randomly through space. Instead, they are linked together in sweeping chains, walls, and sheets, forming vast cosmic patterns with enormous empty voids in between. The galactic South Pole was one of the very first regions of the sky through which humanity glimpsed this majestic web, this hidden architecture of the universe. Yet the South Pole does more than reveal the world beyond the Milky Way. It also helps us uncover secrets about the galaxy itself. By studying how stars and gas thin out as they stretch away from the Milky Way's central disk, astronomers can measure the shape of the halo that surrounds the galaxy. This halo is a faint sphere made of stars and vast quantities of invisible dark matter. It stretches far beyond the spiral arms we see, shaping the Milky Way's gravity and history. When the data from the North and South Poles are compared, astronomers gain a powerful tool for testing the galaxy's structure. If the Milky Way were perfectly symmetrical, the two poles would look exactly alike. But studies show this is not the case. The southern view in particular reveals signs of imbalance. These irregularities may be the fading scars of ancient cosmic collisions. Over billions of years, the Milky Way has not lived alone. Instead, it has drawn in and swallowed many smaller galaxies, a slow but relentless process sometimes called cosmic cannibalism. The stars and dark matter from these consumed systems leave behind delicate trails, ripples and clumps. These remnants are often easier to spot from the clear vantage point of the galactic South Pole. In this way, the southern pole acts like a historical archive, keeping record of the Milky Way's turbulent past and the violent way in which it grew. But the galactic South Pole is not only about history, it is also a crucial tool for present-day science. Many modern space observatories use it as a calibration field. Calibration is the process of checking and fine-tuning scientific instruments to ensure their measurements are correct. Because the polar regions of the galaxy are so clear and uncluttered, they provide the perfect background for this work. Some of the world's most important space telescopes have relied on the galactic poles for this purpose. Galactic, which observed the universe in ultraviolet light. Spitzer, which revealed the hidden world of infrared radiation. Chandra, which focused on high-energy X-rays. And Planck, which mapped the faint glow of the cosmic microwave background. All of them turned to the poles for calibration. The Planck spacecraft, in particular, depended on the galactic South Pole to refine its delicate measurements of the microwave background, the dim afterglow left behind from the Big Bang nearly 14 billion years ago. Without the clear skies of this region, such observations might have been impossible. Adding to its importance, the galactic South Pole is also home to two of the Milky Way's closest companions, the Sculptor Dwarf Galaxy and the Fornax Dwarf Galaxy. These are small and faint galaxies that orbit the much larger Milky Way. Though they contain far fewer stars than our galaxy, they are scientific treasures. These dwarf galaxies are especially rich in dark matter, making them key laboratories for testing ideas about how galaxies form and evolve. By studying the motion of stars within Sculptor and Fornax, astronomers can calculate how much invisible dark matter shapes their gravity. These insights help us understand not only the dwarfs themselves, but also how the Milky Way has been gathering its mass for billions of years. In a sense, Sculptor and Fornax are like living fossils, tiny ancient galaxies that preserve the memory of conditions from the early universe. Their presence near the galactic South Pole makes this region even more valuable. Far below the bright central plane of the Milky Way, the southern sky opens into a region known as the South Galactic Cap. This is not just any patch of sky, it is a high-latitude window into the universe, one that has become a favourite target for astronomers carrying out deep surveys. If the northern galactic cap is like one great observatory balcony, offering views of colossal filaments of galaxies and the enormous stretches of emptiness known as cosmic voids, then the southern cap is its twin on the other side of the galaxy. Together they give us a balanced picture of the universe's structure, like the two halves of a grand puzzle that only makes sense when both pieces are joined. Astronomers cannot build a true three-dimensional map of the cosmos by looking in only one direction. To attempt such a task while ignoring half the sky would be like trying to describe Earth's geography while pretending one hemisphere did not exist. You would know only half the mountains, half the oceans, and half the continents. The galactic South Pole fills in this missing piece. It ensures that our cosmic maps are not lopsided but full, rich, and as accurate as possible. In the past few decades, a brand new branch of astronomy has emerged, one that does not rely only on light. This is the study of gravitational waves, tiny ripples in the very fabric of space and time. These waves are born in some of the most violent events the universe can produce, the smashing together of two black holes, the spiraling collision of neutron stars, or other cataclysmic encounters where immense masses move at incredible speeds. Remarkably, humans have already learned how to detect these faint tremors. Large projects such as LIGO, based in the United States, and Virgo, located in Europe, have caught dozens of these signals. Each detection is a kind of echo from a cosmic disaster that may have happened millions or even billions of years ago. The very idea was first predicted by Albert Einstein more than 100 years earlier, and now, after a century of waiting, his vision has been confirmed. The future promises even more. In the coming decades, space missions such as LISA, a laser interferometer that will orbit the Sun, are expected to open an entirely new chapter, detecting waves from sources that ground-based instruments cannot hear. For this growing science, the galactic South Pole is especially valuable. The polar regions of the sky can be watched for long stretches without interruption, unlike other regions that dip below the horizon. This makes them perfect for continuous listening. In this way, the South Pole is not only a window to light, it becomes a quiet listening post, an ear pressed to the deep rolling thunder of the universe itself. But gravitational waves are not the only reason the South Pole matters. Another great mystery that it helps to unravel is the nature of the Milky Way's magnetic field. These fields are not visible to human eyes, but they are real. They stretch like invisible threads across the galaxy, guiding the dance of charged particles, steering the path of cosmic rays, and shaping the movement of thin plasma that drifts between the stars. Most of the galaxy's magnetic lines follow the graceful curves of its spiral arms, yet some of them rise upward and downward, reaching into the galactic halo that surrounds the Milky Way. By observing these fields from the vantage of the South Pole, astronomers gain a kind of vertical view. It is like stepping back to look at a massive painting not just from the side but from above and below, to understand its full three-dimensional shape. Mapping these fields is not just an academic exercise. They matter because they create foreground noise, a kind of magnetic static that can confuse the faint signals astronomers are trying to detect from the distant universe. The whispers of the cosmos, the afterglow of the Big Bang, the echoes of the first galaxies, the signals from faint clusters, can all be buried under this magnetic hum. By carefully studying the galactic South Pole, researchers can separate this noise from the true cosmic signals, clearing the window to the universe's earliest chapters. In the precise language of science, the galactic South Pole is often described as a control field. Just as a doctor needs a healthy patient for comparison when studying disease, astronomers need clean, relatively empty regions of sky to compare with more crowded and complicated ones. The South Pole provides just that. It is a kind of cosmic baseline, a place against which measurements can be tested and confirmed. With it, astronomers can refine their models of dark matter, checking how this invisible material is distributed across space. They can sharpen their studies of baryon acoustic oscillations, those faint ripples left in the arrangement of galaxies by sound waves travelling through the young universe. They can also confirm whether distant galaxy clusters, barely visible on the edge of our instrument's sensitivity, are truly real or only illusions of background noise. Without such a control region, many of these results would remain uncertain. The South Pole, therefore, acts as the quiet laboratory where the universe itself can be studied with fewer distractions. It is true that the galactic North Pole often receives more of the spotlight in news stories. The famous deep field images, or the cosmic microwave background maps, usually highlight the northern sky. Yet the south is no less vital. Together, the two poles bring balance. They are like the two ends of a scale. Without one, the weight of evidence would tip unevenly. The South Pole mirrors the North. It tells us whether our galaxy is symmetrical or slightly skewed, whether our instruments are well calibrated or drifting out of line. It gives us a second anchor point for measurement, something that strengthens confidence in every cosmic result. Most importantly, it opens access to quieter, cleaner patches of space, where the grand story of the universe can be read in purer form. The galactic South Pole is more than a direction in the sky. It is a reminder that no single viewpoint is ever enough. To truly understand the Milky Way, the sprawling web of galaxies, and the vast architecture of the cosmos, we must look in both directions, north and south, above and below, inward and outward. Only then do we see the full shape of reality. Try to imagine yourself drifting upward, higher and higher, leaving behind the blue skies of Earth, the shining warmth of the sun, and the slow dance of the planets. You rise so far that even the orbiting paths of Mars, Jupiter, and Saturn shrink beneath you into invisible circles. Soon you are so high that you no longer stand on anything solid. You're not on a mountain peak, nor inside a spacecraft. Instead, you float freely in the deep silence of space itself. At this impossible height, Earth no longer holds you. Its curved horizon has faded away, and the word down no longer points anywhere. Here, in the great ocean of the universe, there is no ground, no roof, no walls. There is only a vast black sea sprinkled with countless stars glowing like scattered embers from a cosmic fire. It feels endless, and yet, astronomers, the people who have devoted their lives to making sense of this infinite space, cannot afford to wander aimlessly. Just as sailors on ancient seas needed the North Star or a compass to find their way, astronomers also need a fixed direction. They need a cosmic landmark, something that will never move, no matter where they travel. On Earth, we have the North Pole, the South Pole, and the crisscrossing grid of a latitude and longitude that guides sailors across oceans and pilots through the skies. But what about in space, where there is no horizon and no natural up or down? This is where the idea of the galactic North Pole comes into play. The galactic North Pole is not a glowing star, nor is it a beacon shining above the Milky Way. Instead, it is a point, completely invisible, defined only by geometry, that serves as a cosmic compass. You cannot see it with your eyes, but its importance is immense. By pointing toward it, astronomers decide what direction is above the flat disk of our galaxy. To picture this, imagine the Milky Way not as a cloud of stars, but as an enormous disk, something like a record or a DVD, only stretched out on a scale that is nearly beyond imagination. This disk is wide but very thin, and across it lie billions upon billions of stars, glowing clouds of gas and streaks of dark dust. Now picture yourself taking a pin and pushing it straight through the very centre of this cosmic disk at a perfect right angle. The pin would poke out of both sides. One end of the pin would point upward. That is the galactic North Pole. The other end would point downward. That is the galactic South Pole. The galactic North Pole lies in the direction of a soft, faint constellation known as Coma Berenices, the Hare of Berenice. This constellation is not as famous as Orion with his belt, or Leo with his lion's mane, though Leo rests close by. Coma Berenices is made of gentle, dim stars that look less like a sharp pattern and more like a thin cloud spread across the night. And yet, within this quiet patch of sky, astronomers have anchored one of the most important reference points in the entire universe. Earth's North Pole is not perfectly steady. It drifts slightly over the centuries because Earth itself wobbles on its axis. But the galactic North Pole is far more stable. The Milky Way's great frame remains firm, as if frozen into eternity. It is, in a sense, the ultimate up of our galaxy. Now you might wonder, why does this matter? Why should anyone care which way is up, in a place where up and down do not exist? The answer is that the universe is not a random scattering of stars. It has structure. Galaxies spin like wheels, stars are born in great clusters, black holes tug at everything around them, and invisible rivers of gravity guide even entire galaxies along their paths. To study this grand cosmic order, scientists need a fixed frame of reference. For example, when astronomers measure the tilt of galaxies, track the journey of our own solar system, or investigate strange cosmic mysteries like the Great Attractor, a massive gravitational anomaly pulling entire clusters of galaxies, they must be able to say, we are moving in this direction, at this angle, along this path. Without a standard reference like the galactic North Pole, such measurements would float without meaning. Think of an airplane. A pilot uses pitch, roll, and yaw to describe how the aircraft is tilted or turned in the sky. In much the same way, astronomers need three-dimensional directions to describe how our solar system sits inside the galaxy. The galactic North Pole provides that anchor point. To make this practical, astronomers built something called the Galactic Coordinate System. It works like Earth's system of latitude and longitude. On Earth, the equator divides the globe into north and south, and we measure degrees of latitude from there. Longitude lines run from pole to pole, helping us measure east and west. In the galaxy, the thin, flat disk of the Milky Way acts like the equator. The galactic North Pole is defined as lying at 0 degrees longitude and plus 90 degrees latitude. Its opposite, the galactic South Pole, lies at minus 90 degrees latitude. And here is where things get truly fascinating. When astronomers point their telescopes at the galactic North Pole, the view ahead clears dramatically. The thick clouds of stars, glowing gas, and dark dust that fill the main disk of the Milky Way fall away. Through this direction, astronomers look not through the crowded fog of our own galaxy, but through a much cleaner window of space. This window has become one of the greatest gifts for deep space exploration. Through it, scientists have spotted some of the farthest galaxies ever seen, their light having travelled across billions of years of cosmic history. Without the dust and clutter of our own galaxy blocking the view, the light of these ancient worlds streams through unhindered, carrying stories from the earliest eras of the universe. Looking in this direction has also allowed scientists to map the halo of the Milky Way, a vast ghostly sphere that surrounds the galaxy. This halo is made not of glowing spiral arms, but of thin gases, scattered old stars, and above all the mysterious dark matter that outweighs all the visible stars combined. The halo cannot be seen with the naked eye, but it makes up a large fraction of the Milky Way's hidden mass. Without the clear sightline of the galactic North Pole, discovering and mapping this invisible structure would have been nearly impossible. And still, the usefulness of this cosmic compass does not end there. The galactic North Pole also gives astronomers one of the best views for studying the cosmic microwave background radiation, the faint glow that fills the entire universe, left over from the birth of everything. This radiation is the afterglow of the Big Bang, the event that began the universe nearly 14 billion years ago. To detect this ancient whisper of light, scientists need parts of the sky that are as quiet and uncluttered as possible, not buzzing with stars, dust, and hot gas. The Wilkinson Microwave Anisotropy Probe and the Planck Observatory of the European Space Agency both turn their instruments toward the galactic North Pole for this very reason. By doing so, they could see beyond the stars of today and catch a glimpse of the universe as it was when the first atoms were forming, when light itself was just beginning to travel freely through space. Looking in that direction is like looking back in time across nearly the entire history of the cosmos. Even some of the newest and most exciting branches of science, like the study of gravitational waves, depend on knowing exactly how our galaxy is tilted and positioned in space. Gravitational waves are like ripples spreading across the very fabric of space and time, set off when gigantic objects, such as black holes or neutron stars, slam into each other with unimaginable force. These events are so powerful that they send out vibrations across the universe, yet by the time those waves reach Earth, they are faint and delicate like whispers after a thunderclap. Special observatories here on our planet, including the famous detectors known as LIGO in the United States and Virgo in Europe, are built to catch these almost invisible shivers. But recording the waves is only the first step. To truly understand them, astronomers need to know exactly where they are within the grand map of the galaxy. These cataclysmic crashes do not happen just anywhere. They tend to gather in regions that are heavy with matter, clustering along the hidden framework of the cosmic web. By charting their positions against the directions of the galactic north and south poles, astronomers begin to see patterns that would otherwise stay hidden, like invisible constellations stitched into the universe. At the same time, our own solar system is not standing still. The Sun, along with its family of planets, moons and comets, is slowly drifting around the core of the Milky Way in a majestic orbit. One complete journey around the galaxy's heart takes about 230 million years. To put that into perspective, ever since the age when dinosaurs first walked the Earth, the Sun has managed to circle the Milky Way less than 3 times. Our little world and its parent star are passengers on a cosmic voyage that dwarfs the scale of human history. And this movement is not just about travelling forward. As the solar system glides through space, its angle and tilt toward the galactic North Pole gradually shift. It is as though the Sun and its planets are part of a slow, elegant dance, weaving endlessly through the ocean of stars. Knowing where the galactic North Pole lies today allows scientists to retrace our steps far into the past and predict where we will be millions of years into the future. There is something almost poetic about this. The galactic North Pole is not a star, not a glowing beacon in the sky. It cannot be seen with the naked eye. It exists only because we define it through mathematics, measurements, and careful thought. Yet despite being invisible, it acts as a powerful guide. It is like the silent needle of a cosmic compass, helping astronomers orient their instruments, plot their observations, and even stretch their imaginations toward distant horizons. This naturally sparks a deeper, more wondrous question. What actually lies above the North Pole of the Sun? If we could rise straight upward, beyond the fiery surface of the Sun, past the circling paths of the planets, and beyond the far and hazy cloud of icy comets that marks the edge of our solar system, what would we find waiting for us? The answer is not a wall, nor a ceiling, nor any kind of edge. Instead, we would drift into the vast, unending darkness of the cosmos. Beyond us would lie distant galaxies twinkling like islands of light, blazing quasars shining brighter than whole galaxies, and delicate webs of matter stretching for billions of light years across the universe. Each step farther into this immense expanse would not only carry us outward in space, but also backward in time, letting us glimpse earlier and earlier chapters in the story of the cosmos itself. And through this immense journey, the galactic North Pole would remain a faithful arrow, pointing the way forward into the unknown. It would guide us, not with light or sound, but with orientation and direction, helping us to navigate the grandest mysteries of all. High above the fiery surface of our Sun, beyond the boiling storms that constantly roll and churn across its face, there lies a realm that is both mysterious and immensely powerful, the solar polar regions. These regions are not calm, empty stretches of space. They are alive with invisible energies, places where the Sun's magnetic fields bend and twist like giant ropes pulled tight, always straining, snapping and reconnecting. Here, rivers of blazing hot plasma, streams of charged gas so hot that even the very atoms have been ripped apart, are always on the move, shifting, twisting and flowing outward into space. When you turn your gaze toward the Sun's equator, the story looks different. Dark spots, called sunspots, appear and fade like bruises across the surface, while sudden explosions of raw energy, solar flares, burst outward with astonishing force, hurling radiation and charged particles across millions of miles. But the poles of the Sun tell another tale. They're quieter in comparison. Quieter, yes, but never truly still, and certainly not lifeless. The poles are like hidden engines, quietly but powerfully influencing the entire solar system. What begins above the poles does not end there. It stretches outward, reaching every planet, every comet, and even our Earth, shaping the invisible environment that surrounds us all. The Sun itself is not steady or unchanging. Like a living being, it has a rhythm, a kind of heartbeat, called the solar cycle. This cycle repeats roughly once every 11 years. During this time, the Sun's magnetic field becomes tangled and chaotic, then slowly reorganizes itself, flipping its north and south poles in the process. Imagine a compass where north and south suddenly swap places. This is what happens to the Sun every cycle. One of the calmest points in this repeating cycle is known as the solar minimum. This is the Sun's quiet phase, when sunspots nearly disappear and its magnetic field smooths itself into a simpler shape. At the poles during solar minimum, magnetic field lines straighten and shoot outward into space like tightly stretched arrows. From these poles, invisible but powerful streams of solar wind, rivers of high-speed particles, pour outward across the entire solar system. These streams are not just drifting aimlessly into the void, they are the builders of something enormous, the heliospheric current sheet. This is one of the greatest invisible structures in all existence, an unimaginably vast spiral of magnetic influence that spreads outward from the Sun like the swirling folds of a giant skirt spinning through space. It wraps itself around every planet, every asteroid, every comet, around the entire solar system itself. And this colossal structure begins in large part with the winds that blow from the Sun's poles. In the year 1990, humanity took its first daring step into this hidden world. That year, the Ulysses spacecraft was launched on a bold mission. Ulysses was unlike any other spacecraft before it. Instead of orbiting around the Sun's equator, as most spacecraft naturally would, it was designed to soar high above and below the Sun's poles. For the first time in history, humankind would see the Sun from this extraordinary angle. Throughout the 1990s and into the early 2000s, Ulysses flew over both the Sun's north and south poles, completing multiple orbits and gathering priceless data. What it discovered was astonishing. The winds above the poles were unlike the winds at the equator. At the poles, the solar wind was faster, thinner, and steadier. In contrast, the winds near the equator were slower, thicker, and wildly unpredictable, often shifting speed and direction in chaotic bursts. This discovery was not just a scientific curiosity, it revealed one of the key forces shaping the very boundaries of our solar system. The fast polar wind helps carve out the heliosphere, the gigantic bubble of energy and particles that surrounds everything we know. The heliosphere is not empty. It is a shield, a protective cocoon that pushes back against the most dangerous cosmic rays streaming in from deep space. Without it, Earth and the other planets would be bombarded by deadly levels of radiation. In a very real sense, this invisible bubble makes life possible, and the Sun's polar winds are among the main architects of its shape. Think of the space above the Sun's North Pole as a kind of cosmic gateway. It is the launch point from which streams of energy, magnetic waves, and charged particles set forth into the galaxy. If you were to follow these streams outward, past the orbit of Neptune, beyond even the lonely path of Pluto, you would eventually arrive at the very edge of the heliosphere, the border where the Sun's influence finally gives way to the larger forces of the galaxy. At this faraway boundary, the solar wind weakens, its particles fewer and slower. The Sun's magnetic field, stretched to the breaking point, thins into long, frail strands that begin to twist and mingle with the greater magnetic fields drifting between the stars of the Milky Way. It is here, at this frontier, that the Sun's rule ends, and the wider galaxy takes over. In the year 2012, after travelling through space for more than 3 decades, the spacecraft Voyager 1 reached this very boundary. Launched back in the late 1970s, Voyager 1 had journeyed farther than any human-made object before it. At last, it crossed the invisible edge of the heliosphere, doing so near the Sun's northern side. In a galactic sense, it passed above the Sun's North Pole, becoming the first of our creations to step into true interstellar space. And what lies beyond this edge? A strange and delicate realm called the local interstellar medium. It is a thin, ghostly sea of gas, dust, and high-energy cosmic rays that flows between the stars. At present, our Sun is moving through a particular patch of this medium known as the local interstellar cloud. This cloud is slightly warmer and denser than the surrounding space, pressing against the heliosphere like the wind pressing against a balloon, squeezing it here, stretching it there, reshaping it as the Sun continues its journey. Because the Sun is not standing still but racing through the Milky Way at thousands of miles per hour, the heliosphere is not a neat round bubble. Instead, it forms more like a teardrop, with a blunt nose pointing forward in the direction of travel. Yet, this nose does not sit perfectly straight. It tilts slightly upward, toward the region above the solar system's midplane and close to the Sun's North Pole. This tilt means that many of the strange particles, waves, and phenomena encountered by deep space probes come not from the flat plane of the planet's orbits, but from above, from the Sun's northward direction. In this sense, the North Pole of the Sun is not only pointing upward, it is also pointing forward, toward the future, toward the path our star is carving through the galaxy. If you could rise even higher, leaving the heliosphere behind altogether, the view above the Sun's North Pole would open into the vastness of the galaxy itself. This direction offers one of the clearest windows into the far universe. Unlike many other directions where interstellar dust clouds scatter and block the view, the path above the Sun's North Pole is remarkably clear. Through this opening, astronomers can gaze almost unhindered into the great depths of space. Powerful observatories, such as the Chandra X-ray Observatory and the Planck spacecraft, have taken full advantage of this window. Looking out along this pathway, they have measured faint radiation left over from the birth of the universe, traced mysterious X-ray sources, and mapped distant galaxies shimmering like ancient jewels in the night. Even the strange and ghostly travellers known as cosmic rays, tiny particles that race through the universe at nearly the speed of light and shower down on Earth in a never-ending rain, seem to behave differently when we look toward the galactic north. Careful studies have shown something curious. Just a little more of these high-energy messengers appear to be coming from that direction than from anywhere else. This odd imbalance hints at something hidden and powerful. It suggests that the space above the Sun is not just an empty, silent sky, but a region shaped by unseen structures and energetic events that science has not yet fully unravelled. In truth, The area above the Sun's north pole is a kind of borderland, a frontier where two mighty influences meet. It is not wholly owned by the Sun, nor is it fully claimed by the Milky Way galaxy. Instead, it stands between them, a place of overlap and transition. On one side, the Sun still stretches its power outward, its solar winds and magnetic fields flowing far into the dark. On the other, the vast and ancient forces of the galaxy itself push inward, surrounding and shaping everything in their path. Between these two forces lies a frontier, a cosmic meeting ground where the realm of our star touches and mingles with the domain of the galaxy. It is across this northern frontier that some of humanity's bravest machines have already dared to travel. The legendary Voyager probes built in the 1970s pushed outward in this very direction, carrying human hopes and messages on their way to interstellar space. Voyager 1, in particular, set its course northward, upward and outward, leaving the Sun's embrace behind. And it may not be the last. The American Space Agency, NASA, is now studying a bold new mission called the Interstellar probe. Unlike earlier explorers, this spacecraft would be designed from the very beginning to go beyond the Sun's protective bubble, the heliosphere, and sail directly into the untouched sea of interstellar space. If built, it too would most likely follow the same northward path blazed before it. This corridor above the Sun's north pole is not only an abstract line in the minds of astronomers, it is a real and chosen road that humanity has already begun to walk. From the daring voyages of Ulysses, which explored the Sun's polar regions, to the far-flying journeys of Voyager 1, and perhaps soon to the dreams of the Interstellar probe, our species has been slowly carving a route through this northern gateway into the wider universe. Every step we take along this path carries us farther from the warm cradle of our Sun, and deeper into the endless ocean of stars. To go northward above the Sun is to leave behind the familiar dances of planets, comets, and orbits we know so well, and to step into a realm where the galaxy itself holds sway. It is a passage from the known to the unknown, from the shining warmth of our star to the dark, cold, and mysterious expanse of interstellar space, a journey not only outward, but also forward into the destiny of humankind among the stars. Hidden inside the glowing band of the Milky Way, there lies a structure so mysterious and so grand that most people on Earth have never even heard its name. Unlike the Moon, the planets, or the bright constellations that are easy to spot, this strange feature blends into the background. Yet astronomers have been studying it for many decades, carefully gathering clues, asking questions, and struggling to understand what it really is. To this very day, its full nature remains an unsolved riddle. This enormous ghost-like shape is called the North Galactic Spur. To the naked human eye, it is faint, barely visible, like a thin trace of smoke stretching across the northern part of the heavens. Some stargazers have compared it to a ghostly bridge of dust and light, strung across the stars as though some hidden builder had drawn a line across the sky with a cosmic brush. At first glance, it is almost too easy to miss. The Milky Way itself dazzles with the light of billions of stars, shining in a thick band that cuts the night sky in two. Next to such brilliance, the spur appears weak and shy, like a pale echo. The reason for this faintness is that in visible light the spur is hidden behind vast clouds of gas and dust. These clouds act like curtains, blocking its natural glow from our eyes. But astronomers have learned to look beyond what human eyes can see. They have built instruments that detect forms of light invisible to us: radio waves, microwaves, and X-rays. When they turn these special eyes toward the North Galactic Spur, the picture changes completely. Suddenly, the faint arc leaps into view as one of the largest, brightest, and most dramatic features in the entire sky. In these wavelengths, the spur is not shy at all. It blazes with power. The North Galactic Spur is not just a small local cloud floating nearby. It is enormous on a scale that boggles the mind. When astronomers map it using radio waves, it appears as a long, curving filament, almost like an arc of a giant circle. This arc rises high above the flat disk of the Milky Way, bending upward into the northern heavens, before curving back downward again. The arc seems to begin near the very heart of the galaxy, close to the galactic centre itself, before it sweeps outward across a massive section of sky. its sheer size is hard to imagine. To give perspective, the Moon and the Sun each cover about half a degree in the sky. Some constellations like Orion or Ursa Major stretch across 20 or 30 degrees, but the North Galactic Spur extends across dozens of degrees, many times larger than the familiar constellations. If you could paint the night sky, the Spur would look as though some giant hand had dragged a glowing brush across the heavens, leaving behind a broad, luminous stroke. That brushstroke is the Spur, and it dwarfs almost every other recognizable feature in the firmament. Even after decades of patient work, astronomers do not agree on what the North Galactic Spur really is. Several competing theories exist, and each one paints a very different picture of the Spur's history. One of the most popular explanations is that the Spur is part of what astronomers call a superbubble. A superbubble is a gigantic shell of gas and dust, blown outward by the combined violence of many massive stars dying in supernova explosions. When an enormous star reaches the end of its life, it does not fade away gently. Instead, it collapses and then detonates in a supernova. In a single instant, it releases more energy than our Sun will produce over its entire lifetime. Imagine all the sunlight Earth receives over billions of years, condensed into a single flash. That is the terrifying scale of one supernova. Now picture not just one such explosion, but several, all occurring in the same general region of the galaxy. Their shockwaves would slam into each other, combining into a mighty storm that sweeps gas and dust outward into a gigantic shell. Over time, this shell would form a glowing arc, like a scar across the sky. According to this theory, the North Galactic Spur is exactly such a scar, created by multiple ancient supernovae. If this explanation is true, then the Spur is not just a random arc of dust. It is a cosmic memory, a visible monument to the titanic violence of stars that perished millions of years ago. Long after those stars vanished, their explosive deaths still mark the heavens with a scar large enough to be seen across the galaxy. Other astronomers argue that the Spur is much closer to home, not a galactic-scale feature at all. Instead, they believe it belongs to a structure called the local bubble. The local bubble is the region of space through which our solar system currently drifts. It is not empty. Rather, it is filled with very hot, very thin gas, spread across hundreds of light years. This bubble was also carved out by supernova explosions, but these were relatively recent, perhaps only a few million years ago, and they occurred not far from our Sun. If this theory is correct, then the North Galactic Spur is not a vast galactic loop stretching thousands of light years. Instead, it is a nearby wall of gas and dust, a kind of scar on the edge of the local bubble. In this picture, the Spur tells a story not of distant ancient stars, but of violent events in our own neighbourhood of the galaxy. A third possibility is that both explanations are true. The Spur might be a blend of structures, some local, some distant, layered on top of one another along the same line of sight. If so, then when astronomers aim their telescopes at the Spur, they are actually peering through several overlapping layers of gas and dust. Each layer might lie at a different distance, shaped by different events, and moving at a different speed. This makes the mystery extremely difficult to untangle. It is a little like standing in a valley and trying to sketch the shape of distant mountains, while thick clouds drift across your view. Some peaks are hidden, some appear exaggerated, and others look like illusions. The North Galactic Spur presents astronomers with the same challenge, a confusing, overlapping mixture of structures that may not be easily separated. At first glance, the North Galactic Spur might seem like an obscure curiosity, interesting only to specialists, but it is far more important than that. It plays a central role in some of the most delicate and groundbreaking scientific experiments ever attempted. One of the greatest triumphs of modern science was the discovery and study of the cosmic microwave background, often shortened to CMB. This faint, cold glow is the afterlight of the Big Bang itself, the leftover radiation from the universe's birth nearly 14 billion years ago. To study the CMB, scientists launched satellites into space, including the Wilkinson Microwave Anisotropy Probe, WMAP, in the year 2001, and later the Planck mission, launched in 2009. These missions measured the CMB with astonishing precision, mapping tiny fluctuations in its glow. These patterns allowed scientists to peer back to the very beginning of the cosmos, unlocking secrets about the age, shape, and fate of the universe. But there was a serious challenge. Our own Milky Way also produces radiation at the same microwave frequencies. These emissions can contaminate the delicate signal of the CMB like static on a radio. To extract the true voice of the Big Bang, scientists had to subtract this foreground noise. The North Galactic Spur turned out to be one of the largest sources of contamination. Because it shined strongly in polarized microwave radiation, it left an imprint on the data. Without carefully correcting for its effect, the maps of the early universe would have been misleading or even completely wrong. In other words, without understanding the Spur, our picture of the infant cosmos would be blurred and distorted. This ghostly arc of gas and dust, half hidden in the northern sky, played a key role in humanity's attempt to glimpse the dawn of time. Even now, after more than half a century of study, the North Galactic Spur has not yielded its full story. Every new telescope, every fresh survey of the heavens adds details but also deepens the puzzle. Is it a scar left by mighty stars near the galactic centre? Is it a nearby wall marking the edge of the local bubble? Is it both at once, a layered tapestry of cosmic history woven across space and time? Some scientists wondered if the faint signals coming from the strange arc in the sky, known as the North Galactic Spur, might actually be clues to something far more mysterious: the destruction of dark matter near the centre of our galaxy. Dark matter is one of the deepest puzzles in modern science. Unlike ordinary matter, it gives off no light, no heat, and no radio signals. We cannot see it with telescopes or catch it with our instruments. Yet, its invisible pull shapes the stars, binds galaxies together, and even guides the movement of enormous clusters of galaxies across the universe. It is like a hidden skeleton holding up the grand structure of the cosmos. So, when astronomers noticed a strange glow of radiation near the centre of the Milky Way, some became excited. They thought perhaps it was the result of dark matter particles smashing into one another and destroying each other in a kind of silent cosmic firework. If that were true, it would have been one of the biggest discoveries in the history of astronomy. But as often happens in science, the truth turned out to be less exotic. Later and more careful studies showed that much of this strange radiation was not a signal from dark matter at all. Instead, it came from ordinary, though still fascinating, things like the Spur itself. This taught scientists a valuable lesson. If we misunderstand what is happening in our own galactic neighbourhood, we might leap to the wrong conclusions about the entire universe. The cosmos is already mysterious enough without us confusing local shadows for distant wonders. Yet the Spur still gives scientists a rare and precious gift, a way to study magnetic fields on a galactic scale. Magnetic fields are usually invisible, stretching silently through space like ghostly threads. But inside the Spur, tiny grains of cosmic dust act like compass needles, lining themselves up with the Milky Way's magnetic field. As they do this, the dust releases a very special kind of glow called polarized light waves that vibrate in one particular direction. By carefully mapping this polarized light, astronomers can actually see the hidden pathways of the galaxy's magnetic fields. This is normally one of the hardest things to study in astronomy, but the Spur acts like a natural laboratory in the sky, letting us peek into forces that are usually invisible. In this way, the Spur is not just an odd arc of dust. It is a tool that helps us understand how the galaxy works. Still, the North Galactic Spur refuses to give up all its secrets. It does not behave like a simple curve, nor does it fit neatly into the models astronomers have built of the Milky Way's shape. Sometimes, it seems like nothing more than an illusion of perspective, a twisted cloud of dust that just happens to look like a graceful arc from where we stand on Earth. At other times, it feels like something far greater, a vast and powerful structure whose true form we have only begun to glimpse. The universe has a habit of surprising us, and the real story of the Spur may be stranger than any theory we have so far imagined. There is hope that the mystery will not remain forever unsolved. In the near future, new space missions with advanced instruments will create detailed three-dimensional maps of the entire sky, sharper than anything ever made before. One of these missions is called SphereX, short for the spectrophotometer for the history of the universe, epoch of reionization, and IC's Explorer. With tools like this, astronomers may finally measure the true distance to the Spur, trace its actual shape, and uncover its hidden history. Perhaps they will find that it is the nearby wall of the giant bubble of gas that surrounds our solar system, the local bubble. Or perhaps they will confirm that it is the scar left behind by ancient supernova explosions, powerful blasts from giant stars at the heart of the galaxy. Or, just as often happens in science, they may discover something completely unexpected, something no one had even thought to guess. Magnetic fields are not something we can see with our eyes, yet they are everywhere. They guide the paths of tiny particles, affect the birth of stars, and even protect planets from harmful space radiation. Here on Earth, we live inside a magnetic shield created by our own planet's hot liquid core, and without it, life as we know it would likely not exist. But Earth's magnetic shield is only one small layer of protection. Far above us, surrounding our whole solar system, there is an even bigger shield, the heliosphere. The heliosphere is like a giant bubble blown into space by our sun. It is created by the solar wind, a steady, unseen stream of charged particles that the sun sends out in every direction. This wind never stops. It constantly flows outward, filling the solar system and pushing against the thin matter that exists in the space between stars. Inside this protective bubble, the sun is in control. Its winds and its magnetic fields shape the space through which Earth and the other planets move. But beyond the bubble, the power of the sun fades and something else starts to take over: the forces of the wider galaxy. At this edge, the interstellar magnetic field shows itself. This magnetic field does not belong to our sun at all. Instead, it belongs to the galaxy itself, the great sea of stars, gas, dust, and energy that stretches far beyond what our eyes can see. The edge of the heliosphere is not a sharp, solid wall like the sides of a glass jar. Instead, it is more like the blurry, shifting edge where two oceans meet. On one side is the solar wind pushing outward with all its strength. On the other side is the interstellar medium, the very thin mix of gas, dust, and magnetic fields that fills the spaces between the stars of the Milky Way. When these two forces meet, neither side wins completely. Instead, they struggle in a constant tug of war. The solar wind slows down, becomes disturbed, and finally stops at a border called the heliopause. This is the true edge of the sun's reach, the place where the solar wind can no longer push back against the greater powers of the galaxy. Just beyond this unseen line, especially above the northern pole of the sun, the magnetic field of the galaxy itself starts to bend, twist, and flow through the area. It is here, in this strange border zone, that two unseen powers, the sun and the galaxy, weave themselves together. In the year 2012, humanity got a look at this border unlike any before. A small spacecraft launched all the way back in the late 1970s finally reached the edge of the solar system. This spacecraft was Voyager 1, a probe built to study the outer planets but meant to go much farther. Voyager 1 became the first human-made object to leave the heliosphere and enter interstellar space. For decades, scientists had wondered what this crossing would look like. They thought that when the spacecraft passed the heliopause, the direction of the magnetic field would change suddenly, flipping like a compass needle turning backward. But that was not what happened. Instead of a sudden change, Voyager recorded something stranger and more beautiful. The solar magnetic field did not end at all. It bent gently, twisted, and slowly joined with the galactic magnetic field beyond. It was as though two unseen rivers had met, their currents weaving together into a tangled net of lines that folded, joined, and spun around each other. This finding surprised scientists. It meant that the edge of the solar system was not a clean break, but rather a zone of mixing, a kind of cosmic handshake between our sun and the galaxy. These magnetic fields above the heliosphere are not just background details. They play an active role in the life of our solar system. In fact, they are like both guards and pathways. From the farthest reaches of the universe, powerful particles race through space. These particles, called cosmic rays, are born in violent places, exploding stars, jets of energy from black holes, and massive supernova remains. They travel at nearly the speed of light, carrying huge amounts of energy. The magnetic fields at the edge of the heliosphere decide how many of these particles can enter our solar system. Sometimes the interstellar field blocks them, sometimes it bends them aside, and sometimes it guides them straight toward Earth and the other planets. During times when the sun is active and stormy, its magnetic shield grows stronger, making it harder for cosmic rays to get inside. But when the sun becomes quiet and calm, its shield weakens, and the galactic magnetic field pushes harder, letting more cosmic rays stream in. Scientists have even found that many of these particles come more easily from the direction of the galactic north, above the flat plane of the Milky Way. This is not just theory or guessing. Tools have actually seen signs of these magnetic battles. The spacecraft IBEX, which stands for Interstellar Boundary Explorer, along with the Cassini spacecraft that once orbited Saturn, have spotted a strange glowing shape in the sky. They found a faint ribbon of energetic particles stretching across the heavens, like a scar drawn in light. This ribbon seems to line up with the direction of the nearby interstellar magnetic field. In other words, it is a visible mark left by the unseen forces pressing against our solar bubble. This finding was strong proof that the Sun and its heliosphere are not floating freely or untouched. Instead, they are being squeezed, shaped, and even wrapped by the galactic magnetic fields around us. Yet, despite these findings, the true shape of these magnetic lines is still a puzzle. Scientists are still asking, are the lines neat and smooth, curving gently like the field around a simple bar magnet? Or are they twisted and tangled, knotted by old explosions, stirred by the spinning of the Milky Way, and moved by winds from countless stars? The answer is more than just a matter of curiosity. The way these lines are arranged has a direct effect on the future of space travel. Magnetic fields can speed up particles to nearly the speed of light, or they can trap them in deadly belts of radiation. They can disturb spacecraft signals, expose astronauts to harmful cosmic rays, and even confuse navigation systems that rely on charged particle flows. So how strong are these strange fields? Measurements suggest that the magnetic field just outside the heliosphere has a strength of about 36 microgauss. That is far weaker than the magnetic field on Earth, but it is still strong enough to shape the flows of particles and even affect the shape of the heliosphere itself. Some scientists think that our solar system is now drifting into a new part of the local interstellar cloud, a different patch of galactic matter with slightly different magnetic conditions. If that is true, then in thousands of years the shape of the heliosphere could change. It might shrink or grow, offering more or less protection from deadly cosmic radiation. Over such long times, the very environment of our planets could be changed by the unseen magnetic powers of the galaxy. There may even be a link between our local magnetic field and one of the Milky Way's biggest and strangest features, the North Galactic Spur. This is a gigantic arc of gas, dust, and magnetic activity that rises above the disk of the galaxy like a great arching wave. Some researchers think that the interstellar magnetic field surrounding our solar system may line up with this huge structure. If so, then our solar system could be sitting inside a kind of wide magnetic passage, a channel through which particles, dust, and radiation flow across the galaxy. If this link is real, then our solar system's place in the galaxy is not random, but part of a much bigger cosmic design. To uncover the truth, scientists are already preparing new missions. One of the most promising is the Interstellar Mapping and Acceleration Probe, or IMAP. This mission is planned for launch in the late 2020s. IMAP's job will be to map out how particles speed up at the edge of the heliosphere, and how the galactic magnetic field shapes that process. Its tools will be far better than those of IBEX or Voyager. With sharper vision and more sensitive detectors, IMAP may finally show the true shape and direction of the unseen lines above the Sun. For the first time, we may be able to see not just where our solar system ends, but how it fits into the grand magnetic design of the galaxy. The more we learn, the clearer it becomes that the edge of our solar system is not a quiet border. It is a living, changing frontier, a battlefield, a shield, and a doorway all at once. The heliosphere protects us, yet it is also open to the greater forces of the galaxy. The magnetic fields that twist above the Sun are not still. They bend, weave, and ripple, shaped by the life and death of stars, by the spinning of the Milky Way, and by the restless winds of space. They decide how cosmic rays reach us, how spacecraft travel, and how humanity may one day journey to the stars. Space, it turns out, is not an empty void. It is full of power. And at the edge of the Sun's great bubble, where our star meets the galaxy, The unseen web of magnetism reminds us that we are part of a much larger cosmic story. Far above and far below that bright spiral lies something much bigger, stranger, and harder to notice. Surrounding the Milky Way on every side is a vast, ghostly sphere of matter. It is so thin, so faint, and so spread out that it almost disappears to the eye, like a giant bubble of invisible glass encasing the galaxy. Astronomers call this hidden shell the galactic halo. Though we cannot see it, its invisible weight, its gravity, rules over everything inside the Milky Way. It holds the stars, the gas, the dust, and even our own sun and its planets together, binding them into one great cosmic family. As the Sun, Earth, and the other planets continue their endless journey around the galactic centre, they are not sailing through a cold, empty void. Instead, they drift within the lower edge of this immense halo, brushing against a region whose nature still puzzles even the sharpest scientific minds. The halo is not one simple thing. It is made of two very different parts. The first part is called the stellar halo. This is the portion filled with some of the oldest stars in the entire universe, ancient suns that were born long before our own. Alongside them float mighty swarms of globular clusters. These are enormous, glittering balls of stars, each one packed with hundreds of thousands, and sometimes even millions, of stars bound tightly together by gravity. They are like star cities, bright and crowded, circling high above the galaxy. These clusters are not newcomers. They are the elders of the Milky Way. They have been orbiting the galaxy for billions of years, surviving while countless other stars were born and died. But unlike the stars in the flat disk of the galaxy, which move in neat and orderly circles around the centre, the stars of the stellar halo wander like restless travellers. Their orbits are stretched, tilted and uneven, carrying them high above and below the galactic plane. They drift in strange directions, as though they do not quite belong here, and in truth, many of them do not. These lonely wanderers are like fossils in the sky. Just as fossils on Earth preserve the history of ancient creatures, these stars preserve the memory of long-ago cosmic events. They tell astronomers that the Milky Way was not built all at once. Instead, it grew slowly, swallowing up smaller galaxies piece by piece. Each time a tiny galaxy crashed into ours, its stars were torn apart and scattered across the halo. Every lone star drifting on a tilted path is a survivor of those ancient galactic collisions, carrying with it a story of violence and survival written in its orbit. The second and much larger part of the halo is far more mysterious. It is made of something called dark matter. Dark matter is one of the strangest and most puzzling ideas in all of science. It does not shine like stars. It does not glow like gas. It does not reflect light at all. To telescopes, it is completely invisible, like a ghost that cannot be touched or seen. And yet astronomers are certain it is there, because its pull can be felt everywhere. Even more astonishing, this unseen matter outweighs every star, planet, and gas cloud in the entire galaxy. Scientists believe that more than 4/5, over 80%, of the Milky Way's total mass is locked inside this invisible form. The dark matter halo is enormous. It stretches outward for hundreds of thousands of light years, wrapping the galaxy in an unseen cocoon. We cannot see it directly, but we know it exists because of how it tugs on the stars. If we only counted the visible matter, the stars, the gas, and the dust, the Milky Way's spiral arm should spin slowly, drifting apart like loose threads. But they do not. They spin much faster, tightly bound as though an enormous hidden weight is holding them together. That hidden weight is the dark matter halo, the invisible skeleton of the galaxy, quietly keeping everything from flying apart. Our own solar system sits deep inside the lower portion of this halo. Above us there is not empty nothingness, but a strange space filled with ghostly gas, wandering stars, and the powerful but unseen grip of dark matter. The emptiness here is so thin that its density is far lower than even the best vacuum chambers scientists can build on Earth. And yet, this almost invisible halo is essential to the Milky Way's survival. It acts like a cosmic cushion, gently pressing on the galaxy and helping it keep its spiral shape. Without the halo's influence, the Milky Way might slowly unravel. Small companion galaxies, the tiny neighbours that circle us like bees around a hive, could drift away into the silent wilderness of intergalactic space. but the halo holds them close, binding them like moths drawn to a central flame. High above us, beyond the glowing arms of the Milky Way, lies a mysterious and invisible ocean that most people never think about. Astronomers call it the Circumgalactic medium, and it is one of the most hidden layers of our galaxy's halo. It is not something you can see with your eyes or even with an ordinary telescope, because it does not shine in familiar colours of light. Instead, it gives off a faint glow in X-rays, the kind of radiation that only special instruments in space can detect. Scientists first learned of its existence not by looking at it directly, but by watching the way it bends and interferes with the light of even more distant cosmic beacons, such as quasars. In a sense, it revealed itself as a ghostly shadow written across the sky. This strange halo of gas is unimaginably hot. Its temperature stretches from about 1 million degrees to as much as 10 million degrees on the Kelvin scale, so intense that no solid material could survive if it were placed inside. If a planet, a spacecraft, or even a lump of iron were dropped into it, it would be instantly torn apart and vaporized. The amount of matter in this vast cloud is so great that many astronomers believe it might actually outweigh all the stars of the Milky Way combined. Imagine that. The shining stars we see each night, numbering in the hundreds of billions, may not even equal the mass of this invisible haze that surrounds us. Yet the gas does not form a calm and even shell. Instead, it clumps and gathers, particularly above and below the flat disk of the galaxy, almost as if the Milky Way itself were breathing out fire from its poles. Studying this turbulent medium is one of the greatest challenges of modern astronomy. It is not like a planet that you can photograph, nor a star that blazes against the darkness. Instead, it hides, and researchers must act like detectives, piecing together clues from the faintest signals, the way its particles scatter beams of light, the way it warps the passage of radio waves, and the delicate fingerprints it leaves on rays of light that have travelled from galaxies even farther away. To explore this fiery veil, astronomers have built special observatories and launched them into orbit. Satellites such as Rosat, Chandra, and XMM Newton have provided some of the most important glimpses into this hidden world, detecting the X-ray glow and mapping its shape. But the story is far from finished. New missions are already being planned, including XRISM and Athena, spacecraft that will carry far more sensitive instruments. These next-generation observatories will help us peel back the veil of the circumgalactic medium in greater detail, perhaps uncovering secrets that remain invisible to us today. It might be tempting to imagine the galactic halo as little more than an empty container, silently wrapping itself around the Milky Way like a cloak. But the truth is much more dramatic. The halo is alive with motion, violence, and memory. Rising high above and plunging far below the galactic centre are two colossal structures that look almost like balloons stretching into space. These are the Fermi bubbles, discovered only in the last decade, and they are some of the most awe-inspiring features of the galaxy. Each bubble spans tens of thousands of light years, so large that they make our entire solar system look like a speck of dust in comparison. They are filled with gamma-ray radiation, the most energetic and dangerous form of light known in the universe, far more powerful than X-rays. Their discovery left astronomers stunned. To carve out structures of such immensity would require explosions and outbursts so powerful that they challenge the imagination. The most widely accepted explanation is that these bubbles were blown into being by the monster that lurks at the Milky Way's heart, its central black hole. This black hole, weighing as much as millions of suns, usually hides quietly in the shadows, but sometimes it awakens. Long ago, it may have swallowed a great cloud of gas or even consumed a small galaxy that strayed too close. In doing so, it would have erupted in furious blasts of energy, shooting radiation and winds into space with such violence that they carved out these two gigantic glowing lobes that still shine faintly today. The existence of the Fermi bubbles shows that the halo is not a frozen, motionless structure. It can be shaken, reshaped, and stirred by events that take place in the very core of the galaxy. What happens in the centre does not stay in the centre. It ripples outward into the surrounding halo, leaving scars and signatures that remain for millions of years. And our own story is woven into this vast environment. Earth is not outside of the halo, looking in. We are floating within it. The Sun, along with its family of planets, orbits around the Milky Way's centre, at a distance of about 26,000 light-years. Yet this journey is not like a marble circling flat on a table. Instead, the solar system bobs gently up and down through the galactic plane, riding the invisible tides of gravity like a ship rising and falling on the swells of a cosmic ocean. One complete cycle of this rise and fall takes an astonishingly long time, between 30 million and 35 million years. Over these immense spans of time, the solar system moves through different regions of the halo, sometimes passing through denser clumps of gas, sometimes through more rarefied stretches. Some scientists have wondered if these crossings might influence life on Earth. Could the solar system's passage through thicker regions of the halo disturb the Oort cloud, the vast reservoir of icy bodies at the edge of our system, sending more comets tumbling toward the inner planets? Could the constant immersion in this shifting ocean of energy play subtle roles in long-term climate changes, or even in the rhythms of extinction and survival that mark Earth's history? These questions remain uncertain, but they remind us that the halo is not some faraway abstraction. It may be quietly shaping the destiny of our own world. The galactic halo is, in many ways, the memory and the skeleton of the Milky Way. Its scattered stars and ancient globular clusters carry the records of ancient mergers and collisions that slowly built the galaxy from smaller fragments. Its great reservoir of dark matter provides the hidden gravity that holds the spiral arms together, keeping them whirling in their elegant dance across the heavens. Its searing circumgalactic medium wraps the Milky Way in a fiery shroud, and its towering Fermi bubbles stand as monuments to the restless eruptions of the central black hole. And all the while, it cradles our solar system within its unseen boundaries, tying us into the larger family of the galaxy with an invisible but unbreakable bond. What may seem like an empty void around us is anything but. The halo is a living archive of cosmic history, a guardian of the Milky Way's shape, and a reminder that even the darkest corners of the universe are filled with mystery and energy. It is everywhere, silent yet powerful, waiting patiently for us to uncover more of its secrets. Far above our heads, higher than mountains, higher than the flight of birds and airplanes, and even beyond the paths of satellites that circle the Earth, there exists a hidden but immensely powerful point in the northern sky. This mysterious spot is called the North Celestial Pole. It is not a star, not a glowing planet, nor any kind of object that you could ever touch. It is only a point, a direction in the vastness of space, yet its role in human history has been nothing short of extraordinary. For thousands upon thousands of years, this invisible marker has guided sailors across stormy seas, helped wandering explorers cross deserts and dark forests, and given astronomers the key to unlock many secrets of the heavens. It is one of those quiet marvels of the universe, untouchable, unseen, and yet shaping the way people have travelled, built, and dreamed for countless generations. To understand what this North Celestial Pole truly is, picture our planet Earth spinning like a gigantic child's toy top. The Earth turns around an unseen line called the axis of rotation. This axis passes straight through the planet, from the geographical North Pole at the top to the geographical South Pole at the bottom. Now imagine extending that invisible line upward, far beyond the sky and into endless space. The place where it touches the northern sky is what we call the North Celestial Pole. From where we stand on Earth, this pole appears to be the very centre of the heavens, the spot around which every star of the northern sky slowly turns during the night. When we watch the stars rising in the east and setting in the west, what we are truly seeing is not the movement of the stars themselves, but the steady spinning of our planet beneath them. The stars seem to sweep out grand circles across the sky, while the North Celestial Pole remains fixed and unmoving, holding everything together like the central nail of a giant spinning wheel. Because of this, the North Celestial Pole is far more than an interesting astronomical detail. It is the cornerstone of navigation, the guiding reference point of astronomy, and the very pivot upon which our understanding of the heavens rests. And marking this sacred spot in the sky for us is a star of great fame, Polaris, better known as the North Star. Polaris is not the brightest star in the sky, that crown belongs to Sirius, but its position makes it one of the most important of all. Polaris sits almost exactly above the Earth's geographical North Pole. If you were standing at that icy tip of the world, the star would shine directly above your head, right at the highest point of the sky. To travellers, this meant something magical. Polaris always pointed north. No matter where you stood in the northern half of the world, if you could find Polaris, you could find your way. For countless generations of sailors who dared to cross wild and dangerous oceans before the invention of the compass, Polaris was their lifeline. With storms raging around them and no land in sight, they could look up at this steady star and steer their ships across the Atlantic or the Pacific with confidence, knowing that Polaris never deceived them. On land, explorers wandering through deserts or cutting their way through endless forests also looked for Polaris, trusting it as a natural compass that never failed. Polaris became known as the anchor of the night sky because it barely shifts its position, while every other star wheels around it in perfect circles. In long photographs of the night sky, stars appear as glowing arcs or even complete rings, but Polaris stays fixed, calmly marking north with quiet certainty. And yet, this perfect alignment is not eternal. The Earth does not spin as smoothly as a perfect top. Instead, it wobbles ever so slowly. This wobble is called axial precession. Just as a child's top, when it begins to slow down, starts tracing a wide circle in the air, so too does the Earth's axis trace an enormous slow-moving circle across the heavens. One complete wobble of the Earth takes about 26,000 years, a span of time longer than all of recorded human history. This colossal cycle slowly shifts the position of the North Celestial Pole, changing which star serves as the North Star. About 5,000 years ago, it was not Polaris but a star named Thuban, in the constellation of Draco the Dragon, that shone closest to the celestial pole. Many historians believe that the builders of the mighty pyramids of Giza in ancient Egypt may have aligned their colossal monuments with Thuban, not Polaris. Today, in our own age, the title belongs to Polaris. But in the far future, about 12,000 years from now, another star will inherit the role. The brilliant star Vega, shining in the constellation of Lyra the Harp, will become the guiding star of the North. This means that the honour of being the North Star is only temporary. Polaris may look eternal and unchanging to us, but in the grand rhythm of the cosmos, it is only passing through this role, holding the position for a time before yielding it to another. This slow drifting of the North Celestial Pole is not just a curiosity for astronomers. Its location has practical consequences for science, exploration, and technology. Astronomers use the celestial pole as a foundation for their work. When they align their telescopes with the pole, they can track stars, planets, and galaxies with great precision. Without this steady reference, it would be nearly impossible to keep faint, distant objects in focus as the Earth spins beneath them. Engineers also rely on the North Celestial Pole. Satellites orbiting above our world are oriented using it, and the instruments of spacecraft that journey far from Earth are carefully calibrated with its help. Even down on the ground, many communication antennas and observatories are aligned with Polaris to ensure accuracy. Tiny shifts in the position of the pole are like whispers from the universe, showing us how the sun and the moon tug gently but endlessly on our planet. These tiny movements are not just curiosities. They are measured with great care, and the results are used in some of humanity's most important tasks. They help keep our clocks accurate to the tiniest fraction of a second. They guide space missions across the Great Void, and they even allow scientists to study the long rhythms of Earth's climate, stretching far beyond the span of a single lifetime. Long before the age of rockets and satellites, people already looked to the heavens for guidance. Many ancient builders raised stone circles, temples, and even mighty pyramids so that they would line up with the North Star of their age. But the North Celestial Pole is never still. Over centuries it shifts little by little, and so the star that marks north also changes. Those ancient monuments, once aligned with precision, have become quiet witnesses to the slow but steady drifting of the heavens above. This is why the pole is not just an abstract idea dreamt up by astronomers. It is something far more powerful: a navigator's compass, a scientist's measuring stick, and a bridge linking human history with the eternal sky. From the surface of Earth, the North Celestial Pole acts like the hinge of a gigantic invisible door. Every single night as the Earth turns on its axis, the stars appear to circle around this one point. To the naked eye, the movement looks gentle and subtle, but if you wait patiently, you will see it happen. In a matter of hours, constellations rise in the east, sweep grandly across the sky, and vanish into the west. Through it all, the pole remains steady, unmoving, as though the heavens themselves are dancing around it. Photographs with long exposures reveal this hidden motion in a breathtaking way. In such images, the stars no longer look like single points of light. Instead, they appear as curved trails, graceful arcs of a circle painted across the dark canvas of the night. Every one of these arcs shares the same centre. At that centre is Polaris, the North Star, and the invisible North Celestial Pole. These photographs are living proof that our world spins endlessly, night after night, always circling around that unseen pivot. But the story of north does not belong only to Earth. Our solar system itself has a north, defined by the tilt of the Sun's equator. Yet this does not align perfectly with Earth's north, for our planet's orbit is tilted compared to the Sun. On an even grander scale, the entire Milky Way galaxy has its own north as well, located in the constellation of Coma Berenices, far from the comfort of Polaris. This means that up is a relative thing. What is up for Earth is not up for the solar system, and what is up for the solar system is not up for the galaxy. Astronomers must juggle all of these different versions of north when charting the heavens, or when studying the faint and ancient afterglow of the Big Bang, the mysterious cosmic microwave background that still hums through space. Because of these many poles, astronomers have created three great coordinate systems to find their way among the stars. The first is the equatorial system, tied to the turning of Earth and to the North Celestial Pole. The second is the ecliptic system, tied to the yearly path of the Sun across the sky. And the third is the galactic system, tied to the grand structure of the Milky Way itself. At the heart of this framework lies the North Celestial Pole, anchoring one of the most important maps in all of astronomy. The pole also serves as a delicate ruler against the backdrop of the distant universe. Astronomers track its faint movements with extreme precision, comparing its position to faraway stars that remain nearly fixed over human timescales. These careful studies reveal astonishing details: the tug of the Sun and the Moon as they pull at Earth, the slow shifting of mass in our planet's oceans and air, and even the gradual melting of ancient ice that changes the balance of Earth itself. By watching the pole, scientists refine our calendars, improve their models of climate, and plan daring space journeys where even the smallest error could mean failure. Yet the pole is not fixed forever. Earth's axis slowly draws a great circle in the heavens, a motion that takes nearly 26,000 years to complete. Because of this vast cycle, the view of the night sky changes across the ages. New stars rise into importance, familiar constellations drift, and the very pattern of the seasons shifts. The sky of today is not the same sky our ancestors gazed upon thousands of years ago, and it will not be the sky our descendants inherit thousands of years into the future. The North Celestial Pole is therefore not just a marker nailed into the heavens. It is like the hidden hand that turns the wheel of the stars, silently reshaping the human sky over millennia. When people try to imagine what lies above the universe, the mind often does not wander very far. Most of the time, we picture things that still feel close to us. Some may think of the restless streams of solar wind, forever blowing outward from the Sun in every direction. Others may imagine a lonely frozen planet drifting through the dark, cut off from the warmth of a star. And many picture the thin and gentle mist of cosmic dust, the powder left behind by dead stars, floating quietly like smoke in the shadows of space. These images are familiar, and they belong to what we might call the neighbourhood of the cosmos, the things nearest to our home. But if we take a step back, then another and another, until we are looking from a scale far beyond planets and even beyond stars, the very meaning of the word above begins to change. It no longer means simply the sky overhead. It comes to mean something so huge that it stretches imagination itself. Great oceans made not of water but of galaxies, mighty rivers of matter that flow without end, and invisible tides of gravity shaping the very skeleton of the universe. Our solar system, with its planets and moons, is just a speck of dust inside the Milky Way galaxy, that shining spiral of stars we see as a hazy river of light in the night sky. Yet even the Milky Way is not the end of the story. Our galaxy is only one of many thousands upon thousands, and together they belong to something so vast that it makes even the Milky Way feel small. Astronomers have given this mighty region a name, the Laniakea supercluster. The name comes from the Hawaiian language and means immense heaven. It is a name filled with poetry, and it could not be more perfect. Laniakea is not just a cloud of galaxies drifting in every direction. It is a true structure, a colossal basin of the cosmos where gravity has gathered matter into one enormous system. Imagine the way rivers on Earth behave. Water does not move randomly across the land. Instead, it flows down valleys and around mountains, always following the path carved by the shape of the land, until at last it joins the sea. In the same way, galaxies within Laniakea do not move aimlessly. They follow invisible paths set by gravity, sliding slowly but steadily toward deeper wells of attraction, like rivers of stars pouring into hidden oceans. The size of this supercluster is almost beyond comprehension. It stretches across more than 500 million light-years. To understand what this really means, remember that light is the fastest traveller in the universe, racing through space at nearly 300,000 kilometers every second. And yet, even at that speed, a beam of light would need 500 million years to travel from one side of Laniakea to the other. Within this span lie countless galaxies, each containing billions of stars, all caught in a shared and silent journey, like leaves drifting on the same vast current. At the very heart of Laniakea lies something even stranger, an invisible giant of gravity known as the Great Attractor. We cannot see it. It does not shine like a star or glow like a galaxy. And yet, its presence is undeniable. It behaves like a cosmic whirlpool, pulling galaxies toward itself and bending their paths inward. The Milky Way, the Andromeda Galaxy, and even the hundreds of galaxies that make up the Virgo cluster are all being drawn toward this mysterious centre. They are like streams of water merging into the deeper, darker river of Laniakea. The recognition of Laniakea in the year 2014 marked a turning point in astronomy. Before then, scientists described superclusters mostly by looking at the glow of galaxies and sketching their outlines on star maps. But Laniakea was not revealed by light. It was uncovered in a deeper way, through the study of peculiar velocities, the subtle extra motions of galaxies beyond the overall expansion of the universe. By carefully measuring how galaxies drifted with respect to each other, astronomers began to see a hidden pattern. What once looked like separate clusters of galaxies turned out to be linked together by their motion, all flowing in the same direction. In this way, the outline of Laniakea was traced, not by light shining in the darkness, but by the unseen hand of gravity itself. From our viewpoint inside the Milky Way, much of Laniakea seems to lie above the plane of our galaxy, stretching northward into the heavens. It reaches toward constellations such as Virgo, Centaurus, and Hydra. When we gaze up at those regions, we're not simply looking at stars scattered across the sky. We're staring into the most crowded and powerful parts of our larger home in the universe. Astronomers have long noticed that the northern half of the sky reveals a richer and more complex cosmic web than the southern half. Many of the greatest rivers of galaxies flow northward, carrying evidence of the grand design of gravity. This is not just a poetic truth, it is also practical. Because so much of Laniakea's weight lies above us, many of the world's most powerful observatories point their instruments north. Projects such as the Sloan Digital Sky Survey, the 2 Micron All-Sky Survey, and the Cosmic Flows Project have all mapped these regions. The southern skies, in contrast, are harder to study, hidden behind the bright band of our own galaxy's stars and dust. But astronomers have discovered special windows, such as the northern galactic cap, where the view opens wide and clear. Through these windows, telescopes pierce beyond the Milky Way into the emptier realms, tracing the grand networks of galaxies and voids. Inside Laniakea, astronomers have mapped immense filaments, thread-like structures where galaxies line up like pearls on a string. These filaments act like highways of the cosmos, guiding galaxies toward hubs of gravity. Among these hubs are the Great Attractor and the even larger Shapley supercluster, which also lies within Laniakea's domain. The Milky Way itself is travelling along one of these filaments, climbing slowly upward into the northern regions of the supercluster. It is as if our galaxy is moving along the backbone of this enormous cosmic structure. Proof of this motion even comes from the oldest light of all, the cosmic microwave background, the faint glow left over from the birth of the universe nearly 14 billion years ago. This ancient light carries a tiny difference in temperature across the sky, called the dipole anisotropy. That difference shows that the solar system itself is moving upward, drawn toward the centre of Laniakea. This means our journey is not only a drawing on a star map, it is real, physical, and measurable. And yet, as much as we have learned, our understanding of Laniakea is still just beginning. Ordinary telescopes cannot capture its edges, because it is not defined by light, but by the pull of gravity. Mapping it requires not only enormous observatories, but also powerful computer models and simulations. In the years ahead, ambitious new projects, the Euclid mission, the Vera Rubin Observatory, and the Nancy Grace Roman Space Telescope, will continue this work. They will explore how galaxies interact with dark matter, and how these immense rivers of gravity have changed and grown across billions of years. Far beyond the shining stars we see each night, and even past the glowing galaxies that powerful telescopes can capture, scientists have discovered something truly breathtaking. They didn't find it by looking through glass lenses or peering through observatories, but instead through enormous computer simulations, digital recreations of how the universe grew and evolved across billions of years. These simulations reveal that hidden beneath all the stars, planets, and galaxies we can see, there lies an invisible skeleton. But this skeleton is not made of bones, nor of wood, stone, or any substance familiar to us. It is woven from something entirely mysterious, something scientists call dark matter. Dark matter is unlike anything we know. It is not the kind of matter that makes up your body, the earth beneath your feet, or even the fiery heart of the sun. You cannot touch it, you cannot hold it in your hand, and no light bounces from it into your eyes. Yet, despite being invisible and untouchable, scientists believe it makes up the vast majority of the universe's mass. In fact, it may outweigh all normal matter by about 5 times. Dark matter acts as an unseen scaffold that keeps everything in place. Without its silent pull, galaxies might never have come together, stars might never have formed, and the universe itself would look nothing like it does today. But this strange material is not spread evenly across space like mist. Instead, it twists and stretches through the cosmos in a vast tangled network known as the cosmic web. Imagine an enormous net cast across the entire universe. This is how dark matter is thought to lie hidden in space. Yet this web is no fragile spider's net. Instead, it is built of immense filaments of invisible mass, stretching for hundreds of millions of light years from one side to another. These ghostly strands act like highways across the universe, linking together glowing knots of matter where galaxies are born and gathered into enormous families known as clusters. The pattern, however, is not smooth or simple. Around the heaviest clusters of galaxies, these filaments grow thick and heavy, almost like cosmic ropes tightened by gravity's pull. But in the vast empty deserts of space, called cosmic voids, the filaments thin into faint wispy streams, nearly vanishing into nothing. Some even split into smaller branches, threading deep inside galaxies like hidden veins that guide unseen currents. Our own Milky Way galaxy rests within this invisible design. To us, the Milky Way is a shining spiral of stars, gas, and dust, stretching like a silver river across the sky. Yet behind this beauty, our galaxy is wrapped inside a giant cocoon of dark matter, called a halo. Scientists believe that within this halo there may also be smaller strands, tiny subfilaments, that could even pass silently through the very space where our solar system drifts. These ghostly strands may weave above and below the galactic disk, brushing past our sun and planets without us ever realizing. But how do scientists know that something invisible is there at all? The answer comes from one of nature's strangest tricks: gravitational lensing. Normally, light travels straight, but when it passes near a very massive object, gravity bends its path, as if space itself were made of glass. This bending acts like a natural magnifying lens. Astronomers carefully measure how light from faraway galaxies is twisted, stretched, or curved as it travels toward Earth. These delicate distortions reveal where hidden mass lies. Time after time, the maps drawn from these light bendings show the same thing: a web of dark matter threads stretched across the heavens, tying galaxy clusters together into a vast cosmic net. Some computer models even suggest that our solar system may sometimes pass near one of these hidden strands. Inside the Milky Way's halo float smaller knots of dark matter called subhalos. If one of these invisible lumps ever drifted close, it might tug gently on the orbits of planets, disturb the icy comets on the edge of our solar system, or bend the light from distant stars in a way sensitive instruments could detect. So far, no one has directly seen such a filament near us, but hints are growing stronger. The European Space Agency's Gaia mission, which is carefully tracking the motions of more than 1 billion stars, has begun to notice tiny ripples and wobbles in long streams of stars. These may be the fingerprints of dark matter knots quietly gliding through our galaxy. If one ever wandered close to our solar system, we would not see it shine or glow. Instead, we would only notice it from the way nearby stars, clouds of gas, and perhaps even comets shift ever so slightly under its hidden pull. There is another mystery too. Could these filaments affect the paths of cosmic rays? Cosmic rays are particles racing through space at nearly the speed of a light, carrying incredible energy. Some scientists believe that denser strands of dark matter might bend their paths, or even change their energies a little. If this proves true, then cosmic rays could become yet another tool to map out the hidden structure of dark matter's web. Should we be worried about these ghostly strands drifting through our universe? Almost certainly not. Dark matter is unimaginably thin. Even in the thickest parts of a filament, there might be only a handful of dark matter particles in a space the size of a kitchen refrigerator. To us, that would feel like absolute emptiness. Yet on the scale of galaxies, the gravity of dark matter is strong enough to choreograph the dance of stars, direct the flow of gas, and guide the slow birth of new suns. Over millions of years, dark matter filaments may decide where galaxies grow, how spiral arms shift, and even how clouds of comets like the Oort cloud are stirred at the edge of our solar system. Looking ahead, scientists are building even more sensitive instruments to search for traces of dark matter. One ambitious project is the Laser Interferometer Space Antenna, or LISA, which will try to detect the tiniest ripples in space itself, known as gravitational waves. Some of these ripples may arise from the interactions of dark matter filaments. Another upcoming mission, called CMBS-4, will study the faint glow left from the Big Bang, the cosmic microwave background. By searching for tiny distortions in this ancient light, it may uncover the fingerprints of dark matter structures that first formed when the universe was still young. If these predictions turn out to be true, then the night sky above us holds far more than stars. Flowing invisibly through our galaxy may be entire rivers of dark matter, drifting silently, shaping the Milky Way's future without ever shining a single spark of light. These are the hidden threads of a story still being told, the story of how the universe keeps itself together. When we look at the universe, we picture the familiar family of planets circling the Sun, Mercury shining closest, Venus covered in thick clouds, Earth with its blue seas, Mars red and dry, and then the giant gas planets with their huge storms and frozen moons. Beyond them lies the dwarf planet Pluto drifting in the darkness of the Kuiper Belt. For many, Pluto once marked the very edge of our Sun's realm, but in truth, that was never the end. Far beyond the Kuiper Belt, past the scattered disk where icy pieces wander like cosmic outcasts, lies one of the most mysterious and distant regions ever imagined, the Oort cloud. Picture a giant, ghostly ball, made not of light or gas but of frozen objects, comets, icy rocks, and leftovers from the early days of the solar system. This shell, sometimes compared to a bubble or a cage of ice, is thought to surround the Sun on all sides, marking the farthest reach of its pull. The Oort cloud is ancient, older than human history, older even than the Earth itself, for it was formed when the solar system was still young, billions of years ago. Inside it are thought to rest countless frozen wanderers, each a leftover from creation, waiting silently in the dark until something pushes them inward toward the Sun. But there is a question rarely asked. What lies beneath it? The Oort cloud is usually pictured as a vast, even sphere. But what about its underside? Its southern half that dips below the solar system's main layer of planets, stretching into the far reaches of southern space. Could it be different from the top half we usually imagine? Could the bottom hold secrets untouched for billions of years, or maybe even fragments from other stars. To understand how big the Oort cloud really is, we use a special unit of distance called the astronomical unit, or AU. 1 AU is the average distance between the Earth and the Sun, about 150 million kilometres. For everyday scales, that is already a huge gap. Yet the Oort cloud begins not at 1 AU, or even 100 AU, but at about 2000 AU from the Sun, and may reach out as far as 100,000 AU. Let's put that into perspective. Pluto circles the Sun at about 40 AU. Humanity's most distant spacecraft, Voyager 1, has been travelling outward since the year 1977 and has already passed beyond the edge of the heliosphere, the Sun's protective bubble. Even so, Voyager 1 is only around 160 AU from home. That means it has not even touched the edge of the Oort cloud. To Voyager, the cloud still lies like an unreachable horizon. The scale is so enormous that if the Sun and its planets were shrunk to the size of a coin in your hand, the Oort cloud would stretch outward across an entire city. It is a frontier not only of distance but also of imagination. No telescope has ever seen the Oort cloud directly. It is too faint, too spread out, and too far away. Its icy pieces are small and reflect little sunlight. For us, the Oort cloud is an unseen structure, yet we know it exists. Its presence is revealed by comets, icy messengers that dive into the inner solar system on long, stretched-out orbits. Unlike short-period comets that return every few years, these long-period comets come from random directions, some tilted at sharp angles, others even moving backward compared to the neat paths of the planets. Such wild paths can only be explained if they came from a faraway spherical storehouse, the Oort cloud. Some comets even seem to come from the underside, the southern half of this icy sphere. Famous examples include Comet Hale-Bopp in the year 1995 and Comet C 2017 K2 Pan-STARRS. Both entered the solar system on sharply slanted paths, almost as if they were tumbling down from below. These comets, like postcards from the deep, give indirect proof that the Oort cloud is not a flat disk, but a true three-dimensional sphere surrounding the Sun. This balance brings us to a new question. Is the Oort cloud really the same everywhere, or is its bottom half, the underside, different? Some scientists believe the southern regions may indeed have special traits. One reason lies in the position of our solar system within the Milky Way. The Sun does not sit perfectly centred in the galaxy's flat disk. Instead, it hovers a bit above it. Because of this, the lower part of the Oort cloud may feel the galaxy's pull differently. Over billions of years, such an uneven tug could stretch or squeeze the southern half in ways not matched in the north. If so, more comets might drift inward from the underside than from the top, making the southern Oort cloud a busier, more restless place. The Oort cloud does not float untouched. As the Sun travels around the centre of the Milky Way, taking more than 200 million years for one orbit, it meets other stars. Some pass close enough to disturb the Oort cloud with their pull, stirring its icy members and sending them rushing toward the inner solar system. About 70,000 years ago, a faint red dwarf called Schultz's star came within less than a single light-year of the Sun. Though dim and barely seen in our skies, its closeness was enough to tug at the Oort cloud, likely shaking loose comets, perhaps especially from its southern half. In the future, about 1,300,000 years from now, another star, Gliese 710, will come alarmingly close, within only about 0.06 light-years. Such a flyby will almost certainly scatter countless comets inward. Many of these may rise from the underside of the Oort cloud, raining down like icy arrows from the southern skies. But stars are not the only cosmic players. Some scientists think the Oort cloud may also be shaped by something far more mysterious: dark matter. Dark matter is an unseen stuff that makes up most of the mass of the universe. It does not shine, it does not block light, and it cannot be touched. Yet its pull is real, shaping galaxies and holding them together. Some ideas suggest that thick clumps of dark matter may sometimes pass through the far edges of the solar system, especially from less seen directions like the underside. These meetings could jostle the Oort cloud and send comets tumbling inward in waves. If such showers were big enough, they might even cause extinction events on Earth, just as asteroids and comets have done before. Though uncertain, this thought adds an eerie sense of danger to the Oort cloud's underside, an unseen place possibly tied to the great cycles of life and death on our planet. Another interesting idea suggests that the underside of the Oort cloud may hold not just native solar system objects, but also visitors, icy travellers from other stars. Billions of years ago, when the solar system was young and stormy, countless small planetesimals were thrown outward by the giant planets. Some escaped fully, while others became trapped in the Oort cloud. During this same time, the Sun was part of a crowded star cluster, packed with newborn stars. It is thought that some of their icy leftovers may have drifted close enough to be caught by the Sun's pull. If so, the Oort cloud, especially its southern parts, might be sprinkled with alien comets, frozen fossils from stars long gone. These alien comets would be chemically different, carrying elements and materials unlike those found in comets formed near our Sun. Each one would be a messenger not just from the solar system's edge, but from entirely different stellar nurseries. If we could one day study them, we would be holding pieces of other stars in our hands. The biggest challenge is distance. No spacecraft has ever gone anywhere near the Oort cloud. No telescope has seen it. How then can we know its underside at all? The answer lies in comets themselves. Every comet that falls into the solar system is like a note from the edge of creation. By mapping their paths, astronomers can trace back where they came from. Comets that arrive from steep, southern angles are clues about the underside. By studying their chemical makeup, scientists can compare whether southern comets are different from northern ones. New instruments will make this detective work far stronger. The Vera C. Rubin Observatory, expected to begin its survey soon, will find thousands of new long-period comets in the coming decades. Many of these will come from the southern skies, carrying whispers from the underside of the Oort cloud. Each one will bring us closer to knowing whether the bottom truly differs from the top. Someday, we may go there ourselves. NASA has discussed plans for an interstellar probe, a spacecraft that could travel thousands of astronomical units outward, far beyond the planets. If launched, it could eventually skim the inner edges of the Oort cloud. Such a mission could measure dust, magnetic fields, and the makeup of particles drifting through space, offering the first direct proof about the cloud's nature. By comparing data from above and below, we could finally learn whether the underside of the Oort cloud hides differences unseen from afar. This would be a journey into the oldest frontier of the solar system, a place untouched for billions of years, a place where the sun's strength fades and the galaxy's pull begins. The underside of the Oort cloud is more than just a region of space. It is a frontier where our understanding weakens, where guesswork and science meet. It may hold comets that carry the fingerprints of alien stars. It may be stirred by passing suns and shaped by unseen dark matter. It may be uneven, restless, and alive with comets waiting to fall. For now, it is silent, hidden in darkness. But with every new comet, with every future mission, we step closer to hearing its story. The Oort cloud's underside is not just the bottom of a sphere. It is a doorway to the unknown, the edge of the sun's realm, and perhaps the key to understanding the deeper cycles of our solar system and our galaxy. Far below the familiar flat path that our solar system follows as it circles the Milky Way, there lies a hidden world of space stranger and quieter than most of us imagine. At first glance, one might think that the wide darkness between the stars is completely empty, a hollow nothingness stretching forever. But that picture is not true. Even in the loneliest corners of interstellar space, there floats a delicate haze of gas and dust. This thin, ghostly veil is what our solar system is drifting through right now, and astronomers have given it a name, the Local Interstellar Cloud, often shortened to LIC. The Local Interstellar Cloud is nothing like the thick, heavy clouds we see in Earth's sky. Instead, it is made of a faint mixture of partly charged atoms of hydrogen and helium. It is so thin that if you were placed in the very heart of it, you would see nothing at all. Yet it still stretches across about 30 light-years of space, an unimaginable distance for us, yet only a tiny thread compared to the vastness of our galaxy. And even this cloud is only a small fragment of something far larger, the local bubble, a gigantic hollow in the galaxy's gas and dust. This bubble was carved out millions of years ago by the powerful shock waves of exploding stars, and in its emptiness drift only a few fragile wisps of material, among them our modest local interstellar cloud. But the story grows even stranger when we turn our eyes downward, toward the southern direction of the Milky Way. beneath the thin sheet of the local interstellar cloud. There, astronomers have found an environment more peculiar still, a place even thinner, emptier, and less crowded with matter than the LIC itself. Scientists sometimes call this underbelly of space the intercloud medium. Imagine our galaxy as a quilt stitched together with patches of thick cloth. Some patches are heavy and dense. These are like the rich clouds of gas and dust where new stars and planets may one day be born. But between those thick patches are seams, the spaces in between. These seams are not utterly empty, but compared to the cloth around them, they are astonishingly bare. That is what lies below our current path, a great stretch of extremely thin, low-density matter, the most delicate fabric of space. To truly grasp the difference, think about the numbers. The local interstellar cloud holds about 0.3 atoms in every cubic centimetre of space. That may sound like almost nothing, but on the cosmic scale it is still noticeable. By comparison, the spaces beneath the LIC can sink to only about 0.05 atoms in every cubic centimetre, or even less. That is so close to a perfect vacuum that hardly any particles remain at all. These differences, though they seem tiny, are powerful. They shape the very boundary of our solar system's protective bubble, known as the heliosphere. This bubble is created by the solar wind, the endless flow of charged particles that streams outward from the sun. Eventually, the solar wind slows and balances against the thin pressure of the interstellar gas around us, forming an invisible frontier called the heliopause. Here lies the astonishing truth. The size of the heliosphere is not fixed. If our solar system drifts into a thinner region, the heliosphere can expand and grow outward, since there is less pressure pushing back. If instead we enter a denser patch, the bubble is squeezed inward, shrinking. In other words, the protective shell around Earth and the other planets is alive. It breathes with the galaxy, swelling and shrinking as we move through different cosmic neighbourhoods. Many scientists believe that right now we're close to the very edge of the local interstellar cloud. If so, then in the coming ages, perhaps within a few tens of thousands of years, we may slip into one of those emptier, thinner regions lying beneath it. When that happens, the heliosphere will expand, and more cosmic rays, those high-energy particles born from distant stars and galaxies, will be able to pierce more deeply into our solar system. The change may be subtle, but it matters. Stronger cosmic rays could disturb satellites and spacecraft electronics, and they might even raise health risks for astronauts travelling far from Earth. But how do we know that these regions even exist when the matter inside them is so thin it is almost invisible? The answer lies in starlight, especially the sharp rays of ultraviolet light shining from nearby stars. As this light travels across space, some of it is absorbed by the atoms it meets along the way. By carefully studying these tiny bites of missing light, astronomers can build maps showing where the gas is thicker, where it is thinner, and where the clouds give way to emptiness. Tools like the Hubble Space Telescope and the Far Ultraviolet Spectroscopic Explorer have been vital in this detective work. By studying southern stars such as Alpha Centauri and Altair, astronomers can trace how the local interstellar cloud fades into emptier surroundings. These stars serve as distant lanterns, their light carrying faint but precious clues about what lies between us and them. The birth of these empty regions goes back to violent times. Millions of years ago, giant stars ended their lives in supernovae, explosions so powerful they carved vast hollows in the galactic gas. Over time, several of these blasts, probably happening within the last 10 to 20 million years, overlapped and merged to create the local bubble. This bubble is about 300 light-years across. Inside it, only one small cloud floats, the local interstellar cloud. And beneath even that, we find the emptier stretch of all, a cosmic ghost town. This strange underworld of space is not filled with rich molecules or heavy dust. Instead, it is home to a thin, hot plasma, atoms stripped of their electrons, glowing faintly as they drift in near silence between the stars. If in the future, new missions such as the proposed Interstellar probe or the successors of the legendary Voyager spacecraft venture south of the heliosphere, this empty region will be the first frontier they encounter. Those missions would offer humanity its first direct taste of the intercloud medium, the hidden underside of our galactic home. Though it seems barren, this near vacuum carries enormous value. Its openness allows radio waves and other signals to travel farther and more cleanly, since almost nothing stands in their way. Some scientists have even imagined that if other civilizations exist somewhere in the galaxy, they might use these cosmic corridors to send messages across light years. A listening station placed in such a clear region would act like a high mountaintop radio tower, able to catch the faintest whispers carried from extraordinary distances. So what lies beneath the local interstellar cloud is not chaos but calm. It is the pause between storms, the silence carved by ancient explosions and held still by time. In the southern direction, our solar system is gliding toward the most silent neighborhood it has ever entered. And strangely, this emptiness may tell us more about our galaxy than the crowded clouds themselves. It is the blank page on which the story of stars is written, the quiet space between the lines of the Milky Way's great poem. And as we drift forward, this silent stretch may yet reveal secrets we never dreamed of, not by being full, but by being nearly empty. Rogue planets are perhaps the loneliest travellers in the entire universe. Unlike the familiar planets that revolve around stars, bathing in their warmth and basking under glowing skies, these strange worlds drift endlessly through the cold, silent darkness between the stars. They have no sun to brighten their skies, no steady warmth to comfort them, and no rising or setting of a sun to mark the passing of time. They are like tiny ships lost at sea, sailing forever through an endless ocean of shadows, with no lighthouse in sight. Some of these wandering planets were not always so alone. Long ago they orbited their parent stars faithfully, moving in steady paths just as Earth circles the sun. But the universe is not gentle. Massive gravitational battles, a cosmic tug-of-war between giant planets, or sudden encounters with passing stars can violently hurl a planet away from its home. Thrown out with enormous force, it becomes an exile, cast into the dark void between the stars, never to return. Other rogue planets were born without a star to call home. They formed in solitude, emerging from clumps of gas and dust that collapsed in the darkness, never gaining enough heat or light to ignite a star. From the very moment of their creation, these worlds were orphans, fated to drift alone through space, forever without a sun. Most of these free-floating worlds travel quietly within the broad, flat disk of our Milky Way galaxy, moving among billions of stars like hidden phantoms. Yet some take more unusual paths. They may arrive from above or below the disk, moving at sharp, unexpected angles. A rogue planet entering from galactic north, the region above the flat plane of the Milky Way, comes from a direction that astronomers rarely study. It is like a secret guest slipping in through a hidden door, almost invisible against the vast darkness of space. Spotting these lonely wanderers is no easy task. They are cold, dark, and nearly invisible against the black backdrop of the cosmos. But astronomers have found clever ways to detect them. One of the most remarkable methods is called gravitational microlensing. Nature itself provides this gift. When a rogue planet drifts in front of a distant star, its gravity bends the light of that star. For a fleeting moment, the star brightens and twinkles, almost as if winking at us. That tiny temporary flash can reveal the presence of a world that would otherwise remain unseen. Using this technique, astronomers have discovered rogue planets of all sizes, some no larger than Earth, others many times heavier than Jupiter, the colossal giant of our solar system. The numbers are staggering. Studies suggest there could be billions and billions of rogue planets drifting through the Milky Way, perhaps even more than there are stars. Imagine that. A galaxy not just filled with radiant suns, but also teeming with invisible silent worlds, hiding in the darkness between them. But how do some of these planets find themselves so far above or below the galactic disk? The Milky Way is not a flat, still sheet. It ripples and vibrates like a pond stirred by the wind, constantly shaken by massive events. When galaxies collide or pass near each other, their immense gravity can fling stars and planets from their usual paths. Some are sent so far that they end up in the galactic halo, a vast region of space far above or below the disk. Others may have been torn from small dwarf galaxies or tight star clusters, leaving behind streams of stars, drifting gas, and abandoned planets. Even in crowded star systems with 2 or more suns, chaotic gravitational pushes can send planets soaring high above the disk before they eventually fall back. If a rogue planet were to approach our solar system from galactic north, detecting it would be extremely difficult. Most of our telescopes focus on the galactic plane, or track familiar planets in our system. A dark, frozen world falling straight down from above would be like a shadow slipping silently into a room while everyone stares at the walls. Without a parent star, these planets emit almost no visible light, shining only faintly with leftover warmth from their birth, a whisper of heat detectable only in infrared light. Powerful instruments such as the James Webb Space Telescope or the soon-to-be-launched Nancy Grace Roman Space Telescope can sense that faint glow, but even for them, finding such a planet is like spotting a dying ember in an endless desert of night. Could one of these wandering worlds ever come close to us? The odds are tiny. Space is unimaginably vast, and our solar system is just a small speck within the galaxy. Yet tiny does not mean impossible. Models suggest that perhaps once every few million years, a rogue planet or similar object might pass within just a few light years of the Sun. Even without colliding with Earth, such a visitor could cause disturbances. Its gravity might shake the Oort cloud, the enormous icy shell of comets surrounding the solar system, sending countless comets plunging inward. Like ripples across a pond, waves of icy bodies could sweep into the inner solar system, some potentially heading toward Earth. Some scientists even speculate that this may have happened in the past. A bold idea suggests that the mysterious Planet 9, the hypothetical giant far beyond Pluto, might not be a native planet at all. It could be a rogue planet that the Sun captured millions of years ago, pulled into a long, stretched orbit, hiding in the distant dark. Though uncertain, this theory reminds us that our solar system's history may include encounters with wandering visitors from the galaxy's wild outskirts. Rogue planets also tell a greater story. They are silent markers helping us map the hidden structure of the Milky Way. By studying how these planets move, astronomers can refine their knowledge of the galactic halo, the wobbling disk, and even the invisible pull of dark matter, the mysterious substance forming the hidden skeleton of the universe. Though cold, dark, and silent, rogue planets may hold the keys to unlocking secrets about the very structure of our galaxy. In the coming years, wide-field sky surveys will search for them more carefully than ever before. Missions such as the European Space Agency's Euclid Telescope and the Vera Rubin Observatory will scan the heavens, looking for the faintest flickers of these hidden wanderers, even those arriving from the overlooked regions of galactic north. The night sky may seem filled with shining stars, but in truth, it may be just as crowded with invisible worlds. They drift unseen, like ghost ships across a cosmic ocean. And perhaps, even now, one of these silent travellers is slowly making its way toward us from the darkness above. There might be answers to some of the deepest and most baffling mysteries of the universe, hidden in a strange kind of matter that we cannot see. This invisible substance, known as dark matter, could carry clues about the very foundation of everything we know, about space, stars, and galaxies themselves. Some scientists think that part of this hidden mystery may lie just beneath the flat plane of our Milky Way galaxy, in shadowy and silent regions where even light seems hesitant to wander. To search for this invisible matter, researchers have gone to extraordinary lengths. They have dug underground laboratories far beneath mountains, using the Earth itself as a shield to block out cosmic rays and other interference. They have placed telescopes on mountaintops high above most of the atmosphere, where the air is thin and the skies are clearer closer to the stars. They have even built enormous machines called particle accelerators, capable of smashing atoms together at incredible speeds, in the hope of producing or revealing the elusive particles that may make up dark matter. Yet there might be another realm, less explored, lying quietly just below the organised plane of the Milky Way. In this hidden layer, scientists suspect, unusual particles might move in vast numbers. Among the leading candidates are WIMPs, which stands for weakly interacting massive particles, and axions, a completely different kind of hypothetical particle. WIMPs are thought to be heavy ghost-like particles that almost never interact with ordinary matter. They pass through planets, stars, and even our own bodies without leaving a trace, except for the faint pull of their gravity. Because of this near invisibility, they are strong contenders for being the main ingredient of dark matter. Axions, on the other hand, are imagined to be feather-light, almost weightless. They were first suggested as a solution to a puzzle in quantum chromodynamics, a branch of physics that explains the forces holding atomic nuclei together. But axions may also help explain the universe's hidden mass. Unlike WIMPs, axions could act in very strange ways. They might collect into vast wave-like fields or condensates, and they might interact ever so slightly with magnetic fields, giving them unique behaviour within galaxies. To picture where these particles might gather, imagine the Milky Way not only as a shining spiral of stars but also as a thick disk, swirling with gas, dust and radiation. Most of the galaxy is turbulent. Exploding stars send shock waves through space, newborn stars pour out intense light and radiation, and the central bulge releases powerful storms of energy. Yet, just below the central flat layer, the galactic midplane, there exists a calmer, more tranquil region. It is not as disturbed by violent stellar explosions or intense radiation. This quiet zone, lying at the uniform heart of the galactic disk, may act like a gravitational basin, a place where slow-moving cold particles naturally drift and settle. Over millions of years it could gather thin but extended layers of dark matter, forming subtle structures beneath the plane of the galaxy. Computer models of galaxies support this idea. They suggest that dark matter is not always spread evenly around galaxies like a smooth halo. Instead, it may clump into smaller shapes and patterns. Some of these clumps, called streams or caustic rings, might drift through the galaxy along specific paths. If one of these invisible streams passes near our solar system, it could mean that a steady flow of dark matter particles is passing through Earth, sometimes from below, along upward paths that very few instruments are designed to track. Catching these ghostly particles is incredibly difficult. That is why scientists have created experiments such as Xenon, Lux Zeppelin, and ADMX. These devices are designed to capture the rarest and briefest events, a WIMP striking the nucleus of an atom deep underground, or an axion transforming into a faint photon of light inside a powerful magnetic field. But Earth itself complicates the search. As our planet spins on its axis and orbits the Sun, the angles at which dark matter particles arrive shift slightly. This causes detection rates to rise and fall with direction and season. Researchers are now wondering whether these fluctuations might also be influenced by Earth's position relative to the galactic midplane, especially if some particles are streaming from below. Our solar system does not sit exactly at the middle of the Milky Way's disk. The Sun currently rests about 20 light-years above the galactic midplane. Over time it moves in a slow, graceful up and down rhythm through the disk, like a small boat bobbing on cosmic waves. This oscillation takes roughly 60 million years to complete a full cycle. Right now we're slowly drifting downward, falling toward the galactic underlayer. This descent may be carrying us into regions where dark matter is more concentrated or has different properties than we have ever encountered before. Some scientists think this vertical motion could explain puzzling results seen in certain experiments. For instance, the Derma Libra detector has reported unusual seasonal patterns in its readings, signals that might match the idea of Earth passing through denser streams or sheets of dark matter beneath the galactic plane. In some theoretical models, axions may not float randomly, but instead align into vast filaments or thin sheets. If such structures extend below the Milky Way's plane, they could cross Earth's path at sharper angles than expected, creating bursts of detectable particles at particular times. Beyond these traditional detectors, a new generation of tools is emerging. Scientists are experimenting with quantum technologies, including atom interferometers, devices that use the delicate motion of atoms to measure tiny disturbances, and superconducting microwave cavities, which could sense axion-like particles with far greater precision. One bold idea is to aim such instruments not only along the familiar orbit of the solar system but downward, beneath the galactic disk, toward the quiet southern skies. By looking in this direction, we may finally detect particles that have eluded observation until now. If these instruments succeed, they will do more than reveal the nature of dark matter. They could uncover the hidden structure of our galaxy itself. Instead of imagining dark matter as a simple, smooth fog spread evenly across space, we may discover that it forms an invisible web of filaments and streams, weaving beneath the stars. This unseen architecture could guide the very way galaxies grow, move, and evolve through the cosmos. and humanity, standing on a small planet in the outskirts of the Milky Way, is only beginning to lift the veil on this profound cosmic mystery. When we look at the universe, we often imagine something neat and organised, a great flat disk where planets, moons and comets quietly circle around the sun in smooth and steady paths. In this picture, everything sits nicely on a single level, as if the universe itself were a tidy dinner table. The Earth's own path around the sun, which astronomers call the ecliptic, feels like the clearest example of this order. It is like a line of balance in space, a rule of symmetry that seems to keep everything in its proper place. But this is only the surface of the story. Beneath this thin layer of order lies something stranger, older, and far less studied, a hidden world of chaos and mystery. It is a place where pieces of the past float like forgotten relics, where comets plunge in unexpected directions, and where invisible rivers of gravity twist and pull in ways that go against our neat diagrams. In many ways, it is like an underworld of the solar system, dark, restless, and full of secrets. The best-known members of this hidden world are asteroids and comets. Most of them stay close to the ecliptic, circling along like faithful travellers on a highway. Yet not all follow this rule. Some, especially those that come from the faraway Oort cloud, dive sharply down from above or below. One of the most famous examples is Halley's Comet. Unlike the planets, which all move in the same general direction, Halley's Comet races along a tilted path, travelling backward compared to the planet's motion. Its orbit dips beneath the ecliptic, only to swing back upward again in a grand dramatic arc. Other icy wanderers, such as the dark centaurs or the mysterious Damocloids, behave in much the same way. They slip in at odd angles, crossing beneath the ecliptic like shadows on hidden currents. Many long-period comets, which take thousands or even millions of years to finish their journeys, arrive on paths so steep and unpredictable that they seem almost random. When seen from the side, their travels look like sharp plunges from the southern depths of the solar system. They sweep past the sun in a flash of brilliance, then soar upward again, vanishing into the dark. Though their visits are brief, these comets hint at the enormous gravitational forces that shape the farthest edges of our system. Beyond the icy band known as the Kuiper Belt lies an even wilder area, the scattered disk. This is a wide halo of frozen worlds and broken pieces, many of which rest far below the ecliptic. Some scientists think their strange positions may not be a coincidence. They suggest that a hidden world, a giant planet sometimes called Planet 9, could be hiding out there. This world, still only a theory, might be pulling at these distant bodies, dragging them into steep orbits that dive beneath the ecliptic. If true, then what lies below our familiar solar level may be shaped by the gravity of an unseen giant. But gravity alone does not tell the whole story. The sun and planets are not standing still in space. The entire solar system is moving like a great ship, sailing through the galaxy itself. As we drift along, we create a kind of gravitational wake, sometimes described as a bow wave, in the thin gas and dust of the space between stars. And our motion through the galaxy is not flat. It tilts slightly upward compared to the ecliptic. Because of this tilt, much of the material that drifts below the ecliptic may be more easily disturbed, pulled inward, or dragged by galactic currents as we move through the wider Milky Way. There is also the hidden role of the sun's magnetism. The sun's magnetic field stretches outward in a great spiral, shaped by the rotation of the star. This structure is called the heliospheric current sheet. It is like a giant wavy blanket of charged particles twisting above and below the ecliptic. This current sheet reaches billions of kilometers into space, curling and folding beneath the ecliptic like a flowing curtain. Streams of solar particles and magnetic fields are carried with it, creating a deep and shifting magnetic underworld. These invisible forces bend cosmic rays, scatter grains of dust, and trap drifting particles from the space between stars. Spacecraft have given us rare glimpses into this hidden region. The Ulysses probe, launched in the early 1990s, was built mainly to study the sun's polar regions. But as it moved out of the ecliptic, it also showed how plasma flows and magnetic fields behave far from the solar level. Voyager 2, which crossed just below the ecliptic as it left the sun's influence, recorded strange particle streams, sudden shock waves, and the southern edge of the sun's reach. Its findings hinted that space below the solar system may not be a simple copy of the space above. It may be shaped in a different way altogether. Closer to home, even some near-Earth asteroids carry hints of this hidden order. One striking example is the asteroid called 3200 Phaethon. Its orbit is shaped like a long oval that cuts beneath the solar plane. Because most telescopes are aimed along the ecliptic, where the majority of objects are expected, many tilted bodies like Phaethon may still be hiding, slipping past our searches unseen. And then there is the faint zodiacal cloud, the hazy band of dust made from crumbling asteroids and the trails of comets. To the naked eye, it looks like a soft glow stretching along the ecliptic. But infrared telescopes such as IRAS and WISE have shown that this cloud is not thin and flat. Instead, it has surprising depth, spreading above and below the solar level. The dust beneath the ecliptic scatters sunlight and re-emits it as a faint warmth in infrared light, creating a ghostly glow that most people never see. These telescopes have mapped the hidden dust, showing how it drifts and moves under the combined pull of gravity, the push of solar wind, and the twists of magnetism. So what then lies beneath the ecliptic? Not emptiness, but an entire hidden landscape. It is a world of tilted orbits and crooked paths, of wandering comets and strange pieces, of invisible magnetic waves and subtle galactic currents. It is not simply a mirror of what lies above. It is its own strange, restless world. Here, comets rise like ghosts from the darkness. Here, unseen planets may pull at the edges of reality. Here, the forces of the sun and the galaxy fold and stretch space into shapes we are only beginning to see. Far beneath the broad, flat middle layer of our Milky Way galaxy, far below the plane where most of the bright stars, glowing clouds of gas and glittering dust settle, there exists a part of space that is quiet, cold, and almost empty. Sunlight barely reaches these regions, clouds of gas fade into nothingness, and the familiar hum of star formation seems to vanish into silence. Yet, in this hidden and seemingly lifeless part of the galaxy, scientists believe there may be some of the most mysterious and rare objects in the entire universe. These are known as primordial black holes, often shortened to PBHs, unlike the black holes most of us have heard about, which are born when massive stars end their lives in violent explosions and collapse under their own gravity. Primordial black holes are far older and far stranger. They were never connected to stars at all. Instead, they are thought to have formed directly from the wild chaos of the universe's birth in the very first moments after the Big Bang. Primordial black holes are different from the stellar black holes that astronomers usually study. They could be incredibly tiny, even minuscule, compared to the colossal star-devouring black holes we usually imagine at the centres of galaxies. Some of them might have been no larger than a small asteroid floating through space, while others could have been as massive as a mountain, or even larger. Despite this variation in size, all of them share one remarkable quality. They could be part of dark matter, the invisible substance that seems to make up the majority of the universe's mass. Dark matter does not shine, it does not reflect light, and it cannot be seen with telescopes. It interacts mainly through gravity, pulling on stars, galaxies, and even light itself. In this sense, primordial black holes are particularly tantalizing because, if they exist, they could explain some of the biggest mysteries about the universe's hidden matter. Yet because they do not emit light and are so small, they are extraordinarily difficult to detect. If these tiny cosmic relics are out there, they are quietly drifting beneath the galactic midplane, almost completely invisible, tucked into the cold darkness. To understand where these black holes might have come from, it helps to travel back in time, back to the very first fraction of a second after the universe began, nearly 13,800,000,000 years ago. At that moment, the universe was unimaginably hot and dense. It was not calm, peaceful, or orderly. It was a storm of chaos, with matter and energy boiling and swirling in every direction. Tiny fluctuations in density appeared spontaneously in the cosmic soup, some regions slightly heavier, some slightly lighter. In certain spots, the density became so extreme that it caused a collapse under the universe's own gravity, forming black holes instantly. These were not the product of stars, since stars had not yet formed. They were primordial, born directly from the universe itself, a literal fingerprint from the dawn of time. Depending on the size of the density fluctuations, these black holes could have come in an enormous range of sizes. Some may have been tinier than a single atom, unimaginably small, while others could have weighed as much as thousands or even millions of suns. They are cosmic fossils, relics from an age before stars, planets, or galaxies even existed, a direct window into the infant universe. One of the most intriguing questions scientists ask is why these primordial black holes might be lurking beneath the midplane of our galaxy in particular. The answer lies in the way the Milky Way itself moves and behaves. While we often think of galaxies as flat, neatly spinning disks of stars and gas, reality is far more dynamic. Objects within the galaxy, from wandering stars to massive black holes, do not simply move along a single flat path. They also bob up and down, rising above the midplane and dipping below it in gentle, oscillating motions, tugged and pulled by the galaxy's overall gravitational field. Even the Sun follows such a path. It drifts slowly above and below the galactic plane, completing one full up and down cycle, roughly every 60 million years. Tiny primordial black holes, if they exist, would also move in similar vertical orbits, gently floating up and down through the galaxy. This means that some of them could drift naturally into regions beneath the galactic midplane, places where clouds are thin, stars are sparse, and space is quiet. These regions, far from the bustling centres of star formation and explosive cosmic events, could serve as perfect hiding spots for these elusive objects. These quiet areas are significant because they reduce the background noise of space. The countless bright stars, supernova explosions, and swirling gas clouds that can obscure subtle effects. In these low-density regions, the faint gravitational fingerprints of primordial black holes may become easier to detect. Even though these black holes do not shine or radiate heat, their gravity still affects the universe around them. A massive object, even a tiny black hole, bends the path of light that passes nearby, a phenomenon predicted by Einstein's theory of general relativity. This bending of light, called gravitational lensing, is one of the primary ways astronomers hope to catch a glimpse of a primordial black hole. Essentially, if a PBH drifts in front of a distant star, its gravity acts like a magnifying glass, briefly brightening the star's light as seen from Earth. Careful monitoring of millions of stars can reveal these tiny, fleeting events, like cosmic footprints left by invisible travellers. To catch such subtle signals, scientists rely on advanced surveys of the sky. Projects like OGLE, the optical gravitational lensing experiment, have been scanning millions of stars for years, looking for the telltale flickers that might indicate a passing black hole. Looking further ahead, the Vera C. Rubin Observatory, which will observe the entire visible sky repeatedly over the course of a decade, promises to vastly increase our chances of finding these rare objects. The quiet fields beneath the galactic plane, away from crowded clusters and the bright glare of the central galaxy, may turn out to be the best laboratories in the universe for hunting primordial black holes. In these regions, the subtle gravitational effects stand out more clearly, like tiny ripples on a calm pond, making it possible to detect objects that are otherwise completely invisible. But gravitational lensing is only one way to search for primordial black holes. If one of these ancient objects were ever to pass near our solar system, its presence might reveal itself in even more subtle ways. Its gravitational pull could slightly shift the orbits of asteroids, nudging them ever so slightly off course. It might disturb the delicate paths of distant spacecraft or produce minute effects on the distribution of dark matter in our cosmic neighbourhood. Detecting such tiny influences would require extraordinarily precise measurements and extremely detailed models of the solar system's motion. Scientists would have to track planets, asteroids, and even distant comets with exquisite accuracy. Yet if these small fingerprints could be observed, they would provide direct evidence of something that our eyes cannot see, giving us a rare glimpse into the hidden side of the universe. Primordial black holes, therefore, occupy a fascinating space between theory and mystery. They are not merely hypothetical objects, they are also potential clues to some of the universe's deepest secrets. They could explain dark matter, which has puzzled astronomers for nearly a century, or they could offer insight into conditions that existed only a fraction of a second after the Big Bang. Their tiny or massive forms, hidden under the galactic plane, may carry within them a story that stretches back nearly 14 billion years, a story of creation, chaos, and the earliest structures of the cosmos. Thinking about primordial black holes also challenges our imagination in profound ways. When we picture black holes, we often imagine enormous star-devouring monsters lurking at the centres of galaxies, surrounded by swirling clouds of gas and emitting powerful jets of radiation. Primordial black holes, in contrast, are far quieter, far more elusive. They do not announce their presence with roaring accretion disks or brilliant X-rays. Instead, they drift silently, often alone, in the dark spaces between stars and below the plane of the galaxy, shaping the universe in ways we can only infer. They are cosmic ghosts, a hidden population that might be countless in number, yet almost impossible to see directly. Scientists continue to debate the properties and abundance of these ancient black holes. Could there be many tiny ones, so small that millions of them pass through the space of our solar system unnoticed every year? Could some of them be enormous, rivaling or even exceeding the mass of the larger stars? The answers depend on conditions that existed in the earliest moments of cosmic history, conditions we're only beginning to understand through theory, observation, and computer simulations. Each new discovery, each new measurement of gravitational microlensing or subtle orbital deviations could help us uncover this hidden population and shed light on the universe's earliest chapters. In addition, primordial black holes may influence other cosmic phenomena. For example, they could play a role in the formation of galaxies, acting as seeds around which matter gathers. They might even collide with one another, sending out ripples in the fabric of space-time known as gravitational waves. These waves, detected by instruments such as LIGO and Virgo, offer yet another indirect way to observe these objects. While we may never see them shine, we can watch for the effects of their presence across vast stretches of space and time. In a sense, primordial black holes represent a bridge between the very beginning of the universe and the cosmos we see today. They are relics of an ancient past, fossils that carry the memory of conditions that existed before the first atoms formed, before the first stars ignited, and before the first galaxies spun into life. Studying them is not just about counting black holes or solving the puzzle of dark matter, it is about understanding the birth of the universe itself. They remind us that even in the quietest, darkest regions of space, the universe is full of hidden stories waiting to be discovered. Beneath the galactic midplane, therefore, lies a secret landscape, invisible to the naked eye, where primordial black holes may drift through the cold emptiness. In these hidden zones, where starlight fades and clouds of gas thin out, the ancient ghosts of the universe may silently roam. They are hidden from our ordinary view, yet their influence is profound. They shape the gravity of the Milky Way, bend the paths of distant starlight, and perhaps even hold the key to understanding the invisible dark matter that forms the backbone of our galaxy. Their existence challenges our notions of what is common and what is rare, what is visible and what is hidden, and what is natural versus what is primordial. These black holes are tiny or massive, ancient or eternal, visible only through the subtle effects of gravity, and yet they may tell the story of the universe in ways no other object can. Another possible hint comes from faint gamma-ray signals. Stephen Hawking's theory suggests that black holes can slowly shrink by giving off a tiny trickle of radiation, a strange effect of quantum physics now called Hawking radiation. If primordial black holes are indeed evaporating, they might be quietly releasing weak gamma rays into space. The southern half of our galaxy, which is calmer and less crowded than the northern half, offers a particularly good place to listen for these faint whispers of energy. Some researchers have even proposed that certain mysterious gravitational waves, ripples in the fabric of space-time first spotted by the LIGO and Virgo detectors, could be the result of collisions between two primordial black holes. If these ancient black holes tend to gather in sparse, low-density regions, then the darker, quieter underside of our galaxy might be a hotspot for such crashes. The echoes of these cosmic encounters would then ripple across the universe as ghostly vibrations, the only traces of events that we cannot see directly. If primordial black holes make up even a tiny fraction of dark matter, Earth itself may sometimes pass through streams of them as it drifts along its orbit around the Milky Way. At this very moment, our planet is moving downward toward the southern side of the galaxy, possibly heading into a hidden realm where gravitational jolts and strange cosmic disturbances linger in the dark,